Okay, I think it's time for us to start. Hello again, everybody. My name is George Carapis, and we are on. Okay, let me see, I'm on the right thing. So you guys are watching or participating in the tutorial on learning graph neural networks with deep graph library. So this is a tutorial that was organized by a group of us. Most of us, actually all of us, are affiliated with AWS Deep Learning. And it's actually a team that consisting of people in Palo Alto and people in Shanghai, China. Now, for those you guys who came up late, I would like to make sure that you guys saw that opening screen over here. So the key thing here is, excuse me, for you guys to send an email to that email address, dgl-www at request-nb.mxnet.io. In order to get instructions and links in terms of on how to access the Jupyter notebook in order to be able to do the hands-on tutorials that will be be part of this tutorial. Now, okay, so in terms of the agenda of the tutorial, so we're going to have two 45-minute presentations. The first one will be given by B, and will be or give you guys an overview of graph neural networks. The second one will be given by Professor Zhang, will be on provide an overview on deep graph library. Then there is, according to the schedule, a half-an-hour virtual coffee break, so you guys can go have some coffee or tea or whatever is your preferred liquid. And then there will be three hands-on parts of the tutorial. So one will focus on GNN models for basic graph tasks. Then, according to the schedule, is a lunch break. Then there's a hands-on tutorial on how to train GNNs on large graphs. And there's another half-an-hour coffee break. And then after that, it's going to be the last hands-on tutorial that has to do with GNN models for real-world applications. Okay. So now in terms of mechanics, so on the if you guys go to the GitHub page that is linked from the conference tutorial website, you'll see somewhere at the bottom there is a community link that you can use, I think, to join the Slack channel. That you can potentially use it for asking questions. But I think the easiest way to do it is actually to just use Zoom's own chat channel for posting questions, during both during the presentations and also towards the end during the Q&A portion of the talk. I mean, after the talk is done, and the idea is for us to go through those things towards the end. Okay, so I have about 30 or so minutes, 35 minutes left. So as I mentioned, my name is George Carapis. I'm actually a faculty at the Department of Computer Science and Engineering at the University of Minnesota in Minneapolis. I'm currently on leave though from there, and I'm with AWS Deep Learning Science, based out of Palo Alto in California. And what I'm working on is on the DGL library and on graph neural networks. Okay, so my goal over here is to give you guys a kind of a very gentle overview about graph neural networks. And for those who know what graph neural networks are, this is more of a kind of probably a refresher. For those who are not familiar with graph neural networks, we'll give you some kind of a high-level idea about what they are. Okay, so I would like you to kind of initially focus on kind of three kind of problems, and then see how those problems are relevant for the problem of graph neural networks. Okay, so the first problem that I'm facing is that, or application I'm facing, is that of excuse me, is that of the domain of fraud and abuse, right? And the goal over here is I would like to be able to detect malicious accounts, identify fraudulent financial transactions, find fake reviews, identify fraudulent insurance claims, and so on. Okay. Now, the second application area I would like you guys to focus is out of recommendations, right? So the idea over here is to be able to recommend products, media, article, experiences, jobs, courses, spouses, if we're in a dating site, right? To different individuals, right? And the third kind of application is out of marketing. And from a marketing standpoint, the problems I'm interested in is, for instance, determining who should get a discount, identify, who are the influencers, who is at the risk of churning, and so on. Okay. What is common among all those three problems is that there is, for each of those, there is a graph that underlines the data, or the data can be modeled via graphs, right? And in the context of fraud and abuse, for instance, in a financial setting, that graph will correspond to the graph of financial transactions. Okay, and being able to identify, the fraudulent cases over here is to be able to identify which of those links corresponds to fraudulent transactions, or which of those entities correspond to fraudsters. The council recommendation, there's the data behind many of the recommended systems can be viewed in the form of a graph, and that graph usually has the users and the items. So let's say in the movie setting, I'm going to have a bunch of users over here and a bunch of movies, and a particular user will have rated the movie, indicating by, let's say, given that movie a rating of 5, right? But also for the movies, what I have a lot of other information associated with them. You can think of that as some sort of a knowledge graph describing the movies, right? And also at the same time, what I have a bunch of other attributes describing the users, right? So I have, what I will refer to as a collaborative knowledge graph, right? That can describe the data, right? And that information can be used to, for instance, drive those recommendations. And within the context of a marketing, quite often I have the notion of a social network, right? That tells me, how people interact with each other, how do people get influenced by each other, and so forth, right? So this is a graph that I have, and I often leverage in order to solve, these kind of marketing problems I have defined over here. Okay, so in those three applications, fraud and abuse, recommendations, and marketing, right? So we have the case in which a lot of the underlying data can be modeled via graphs, and solving those problems, right? Give rise to what is referred to as learning tasks on those graphs. Okay, so we're getting the problem of graph learning, and within that area there are three prototypical tasks I would like to be able to solve. Right, one is that of classifying a node, which is in the context of fraud and abuse, identifying which are potentially the malicious accounts if the nodes of that network corresponds to an account. In the context of a marketing, then the task is trying to identify the right customers. Right, so again, classifying a node in a social network as being a potential customer node or not being a potential customer node. Then I have the problem of link prediction. The idea is trying to be able to predict whether or not two nodes in my network can be connected via link. And the task over here, I can formulate the problem of recommendation as out of a link prediction, identifying a missing link between the users and the movies, indicating that a particular user will most likely watch a movie and like it. Right, and also another case of a link prediction task is that of predicting missing relations in the knowledge graph. Okay, and then the third task that I have in the context of graph learning is that of graph classification, and the goal over here is to be able to predict a class for an entire graph. And the prototypical use case for that is, predicting the property of a chemical compound, right? So if I have a chemical compound over here, a common way of representing the chemical compound is via its molecular graph, and then my task is to classify, that graph, whether or not it will bind or not bind to a particular protein, or another task is I would like to compute a numerical value associated with that graph, right? That corresponds to a particular, physical chemical property that compound may have. Okay, so those are the three tasks that quite often arise when we think about learning on graphs. Okay, and a common way of solving, most of the graph learning problems, okay, is is to use a kind of a two-step approach to some extent, right? So the first step is to append the nodes of the graph, right, or the edges or the entire graph, right, into a low-dimensional space, okay? And as part of the embedding process, I'm going to capture the essential task-specific information, right? And once I have that embedding, then I have at that point in time a traditional feature-based representation of the graph. Then I can use off-the-shelf classifiers to solve any of the previous classification problems that I described, right? So this is a case in which if my goal is to solve a node classification problem, I have a graph over here. I learned some way of embedding the nodes of the graph into a point in a high dimensional space, right? So think of like I have some sort of an encoder for the vertices, right? And once I have a high dimensional representation of every vertex over here, then I can feed those things into a standard classifier, okay? And then I can build and then I can solve, for instance, the problem of doing a node classification. Okay, so this is kind of a standard way of solving those learning on graphs problems. So in terms of the traditional graph learning approaches that follow that paradigm, so the first one, and it's probably the one that was is more extensively studied, is that of generating embeddings by doing some sort of a manual feature engineering. Okay, so for example, in the context of a drug discovery, right, a widely used approach of coming with that manual feature engineering is a method called Morgan indexing that compute a bunch of physical chemical descriptors, right, of the chemical compounds, and then I use those descriptors to build classification models. Okay, the drawback of an approach like that is that it requires significant domain expertise. It involves considerable manual fine-tuning. It's time-consuming and usually does not scale. So to address those problems, there's a set of automated approaches have been developed to compute those embeddings that to a large extent rely on unsupervised dimensionality reduction approaches, right? There are methods that fall in the category, I think, like singular value decomposition, tensor decomposition, cofactorization, deep walks, etc. So those are in general quite effective, and in the sense that they can capture certain characteristics of the topology of the graph or of the data. However, they're very not as effective, and many of them cannot even take into account potentially rich attributes, right, that may exist in the nodes. Okay, most of those things tend to employ mostly linear, and in the case of tensor approaches, multilinear models. And they do not really allow end-to-end learning. I mean, those approaches are based entirely on unsupervised dimensionality reduction approaches. So the question is, can we do better? And this is where graph neural networks come into the picture. So what a graph neural networks are is a family of deep neural networks that learn node, edge, and graph embeddings. Okay, and kind of at a bird's eye view in terms of how GNNs work. So if I want to learn an embedding for the target node over here, the red node, what the graph neural networks do is they look at the ego network around that node, right? And ego network is a subgraph, right? That includes all the vertices, right? That up to L hops away from the target node. So I have drawn over here. So this is a 2-hop ego network. So this is all the nodes that they are within 2 hops of the target node. Okay, and then they learn an embedding. So given the target node and that ego network, they learn an embedding that takes into account, right, that subgraph here, right, that includes both the topology of that subgraph and also the different attributes that may be associated with the nodes and the edges of that subgraph. Excuse me. And then the other good thing about that is that the embeddings that they learn for the target node, essentially how that information in that ego network is taken into account, is learned in an end-to-end fashion, right? Based on a particular downstream prediction task. right? For instance, if I want to solve a node classification problem, then the way that information of that ego network is taken into account is done in such a way so that will optimize the classification performance of that node classification task. So graph neural networks, some of the early papers appeared back in 2014, 2015 timeframe, and they have since I haven't exploited. So this is a chart that unfortunately we haven't updated since 2018. But if you can see, you have an exponential increase in the number of GNN papers, right? And the popularity of GNN-based methods, continues to improve. Excuse me, it continues to increase. Now, there have been a couple models that have been developed to formalize how graph neural networks work. And probably the most popular one is the one that is based on the message passing framework. Okay, and the idea behind that framework is as follows, right? So, so look at that picture over here. And what I want to do in that picture is that I would like to be able to compute a representation for the node V1, right? And that representation needs to take into account the representations of its immediate neighbors, okay? So I will assume that for each immediate neighbor, I already have some representation. I represent each of those neighbors, right? Via some vector, right? So let's say for V2, I have a vector H2, for V5, I have a vector A5, and so forth, right? And then also, I will also assume that for every edge, I have some vector associated with it, that captures some of the features of those of that edge, right? And again, what I want to say, there's a vector associated with every vertex, and you can think of that as some sort of an initial set of features or some sort of an intermediate representation that I have, right? Now, what I want to do is I want to use all that information of my one-hop neighbors, right, to compute a new representation for V1. Okay, so in the message passing, formalism, the way the thing is done is as follows: is every vertex over here that is, that points to V1, right? Sends a message to V1. Okay, those messages are aggregated. Okay, and then the aggregated message is used to update the representation to compute a new representation for V1. Okay, so mathematically, the way that thing is done is as follows, right? So I have every vertex W, right, that is in the neighborhood of V. So this is a particular vertex V. So each one of the incoming, vertices, right? So they send a message, right, that is a function, right, of the representation of those vectors of the two endpoints of the vertex of the edge plus the edge features. Okay, and this is some sort of a message function, right? When I'm sending a message, so there's a message that I send. So this is a learnable message, right? Now, so those messages and they're aggregated, right? In the particular case, I aggregate those messages, using just a simple summation, right? But I can do that aggregation with using any function, right? That is permutation invariant. In other words, that I can, aggregate the messages of my neighbors, irrespective of the order in which I will aggregate those messages, so we get the same result, right? And given that, so this is the aggregate message, right, that I got from everything. And then what happens is I use those messages that I received, right, the aggregated messages, right, plus my previous representation, these were the things over here, to derive a new representation for that particular vertex V1. Okay, so in this particular case, so the H vectors over here are the prior representations. E over here, it's the edge representation. M and U, those are learnable functions, right? That they are learned in order to give me a representation, the updated representation for target vertex V. Okay, and again, when kind of said those functions M and U, those are learnable functions. So those can be nonlinear functions that they are learned, and the learning is done in an end-to-end fashion, right? And we'll get to that, in the later on slides. Okay, so that kind of simple idea can actually be represents a single layer of a GNN. Okay, but we can potentially stack multiple layers together. Okay, And this is usually something that gets complicated once you start to visualize. So I'm going to try to take a crack at it here, but that would be a slide that we have to go slowly through here. Okay, let's assume that I have the target 0, that node over here. Now I would like to compute each representation, right? By taking into account, doing it through 2 layers of that GNN, of that message passing process. Okay, so so the first layer, right? What I'm going to do is I'm going to focus on all the nodes, right? That they are incident on that node 0, right? So I'm going to focus on node 1, right? And the node 3 over here, okay? As well as node 4, okay? So now node 1, I would like to see all the, how its representation is updated by taking into account the representations of their incoming neighbors, right? So that node 1 over here, corresponds to that part over here, okay? And what I have over here is I have, it's 6, 5, and 4. 6, 5, and 4 are the vertices that, that they're, incident on 1, essentially the incoming edges of 1, okay? And what those things are going to do, they're going to be send messages, right, to that node 1, right? Those messages will be aggregated. And then that aggregated message, along with the previous representation of that particular node, will be, used to give me the updated representation of that node, right? So that H1 superscript 1 is the representation of node 1 after the first level message passing from its incoming neighbors, okay? So this is what I have over here, right? I do the same thing for 3, right? Which is that vertex over here. So that has only 8, so we'll get just information from 8, right? And I will do the same thing for 4, which has no neighbors, so nothing happens over here, okay? So, so then what is happening then, at the same time, I will also be updating the representation from 0, right? As a result of the first level. So for that one, what I'm going to get is I'm going to get the representation of 1, that is over here. So this is the initial representation of 1, the initial representation of 4, and the initial representation of 3. Messages will be sent over here, aggregated, and then updated to give me the initial representation of 1, right? So what after the first layer computation have been done, right? So what I have initial representations for vertex 0. Essentially every vertex over here, right? I will have an updated representation, right? So the only thing that I have shown on the computation is just for vertex 0, vertex 1, and vertex 3. Okay. Now in the second layer, I do exactly the same thing one more time, right? The only difference is that the messages that they're involved, and I'm just going to look only for that node 0 over here, right? Now I'm looking at the representation that I have just computed, right? So for H1, right, I will be sending from 1 to 0, right? So that along that edge, the message will involve the superscript 1 representation, the representation I have just computed, and I'm sending as a message. And for 4, the representation I just computed, right? Which, by the way, the representation just computed for 1 will be coming from an update function, right? In which the message is empty, right? So that would be the representation of H sub 4, coming out of the first layer, right? And over here, I'm going to have the representation I have computed over here, right? After the first layer, right? So those things will come over here, we'll aggregate them and use those things to compute the updated representation for H0. And this is the output of the second layer, right? Now you can see what happens as a result of that second layer, right? So 0, right, for that second layer will be a function of the first layer's 1. And the first layer 1 is a function of the quote unquote 0th layer 6, right? And the 0th layer corresponds to the initial features associated with those nodes. So you can see after a 2 layer of that GNN, the state, the representation for node 0, right, will depend on the representations of, will take into account information from its first hop neighbors, 1 and 3, right, as well as from its 2 hop neighbors, which in this particular case is going to be 6, 5, 4, 3, and 8. Okay, and that gives me kind of the second is the output after running a 2-layer GNN. Okay, so this is kind of going back to the previous picture that I show you guys over here, that sorry for the backup, that the representation of that node after going through a two-layer, right, takes into account information from that ego network, right? And the way that information is taken into account is not in that kind of structured message passing way of repetitively doing an aggregations over the neighbors, right? But each time that aggregation contains the aggregations of the aggregation and so forth. So after doing it L levels, I'll be able to reach out to information that's L hops away in the network. Okay, so so now why are graph neural networks better than the traditional approaches for tackling that problem? Okay, so there are a couple of reasons for that. Actually, there are 4 reasons that I list over here. So the first one is that graph neural networks compute node embeddings using both the structure of the graph and the features of the nodes and the edges. Okay, so if you guys go back to that feature, so those 0 superscript representations, those correspond to the representations involving some initial features on the nodes, and those things are propagated up. Now, in the context of a recommender system, the graph over here will correspond to like a user item or user book bipartite graph, right? And every user can have a bunch of features over here, right? And every book, excuse me, can have a bunch of features over here, like title, author, type, price, and so forth, right? So when I do that message passing in a GNN, and I go first layer, second layer, third layer, I will be aggregating information, right? Not only based on the connectivity of that, in other words, which are the books and how many books and which other authors, other users have read the same book, right? But it will also be, take into account information about the actual features of the nodes and the edges, right? So this is something that, for example, an approach based entirely on the topology or entirely on the non-zero sparsity structure, like for instance, a singular value decomposition in the user book metrics, right, cannot take into account. Okay, that approach only relies on the non-zero structure, essentially the topology of a bipartite graph, but it cannot blend topology and features in a way that will maximize downstream performance. So why are better? So GNNs can integrate topologically distant information in nonlinear fashion, right? So this is the picture that I mentioned to you before, right? So those message passing functions, right, and the updating functions, right? Those things can be nonlinear functions, right? And usually are nonlinear functions, right? So that you can have topologically distant information aggregated in a nonlinear fashion. So the graph neural networks, are essentially trained in end-to-end fashion. And traditional ways of doing things like an unsupervised dimensionality reduction, usually what I have is I have some sort of a network, let's say, of individuals, and then I do some sort of a kind of an unsupervised dimensionality reduction, right? And once I have a representation of those things, right, and then I have some labels, right, and then I do a classification based on those labels, right? On the other hand, a GNN looks all of those things at the same time. It actually goes from here, computes the representations as representations, and fed into a classifier. A last gets computed over here, and then the whole thing back propagate all the way back to essentially both improve to update the model parameters for the classifier, and also update the representations that will lead to better classification performance. Okay, so the end-to-end training of representations with the downstream task is a key advantage of a graph neural networks. Okay, so the other part of a graph neural networks is that they can actually be trained in an inductive fashion. Okay, which what it means that instead of just learning representations of individuals, right, I actually learn functions that compute representations of nodes in the graph based on the features of the neighbors, right, and the structure, the topological structure of the neighborhood. Right? So it does not depend on which the neighbors are, but what are the characteristics of those neighbors. Okay. As a result, that I can estimate the same GNN model and apply it to compute the embedding, the representation for every individual. And the advantage of that is if I can train that model using a subset of my data, and then if some new node comes into my data, then I can just apply the model I have just estimated, right, to compute a representation for that individual without having to actually go and retrain it. Okay. So there have been. So this is kind of a quick overview about what are the GNNs and what are the advantages. And I have really about 10 minutes left. And so I would like to quickly go through a couple kind of popular graph neural network architectures to give you guys a flavor in terms of how the things are. So the simplest one is actually the graph convolution network, and in that network, the message, the point-to-point message function is nothing more than essentially I'm just sending my representation, right? So for example, for this particular node over here, right? If I want the message I will be receive from each neighbors will just be the previous representations of those nodes, be sent over, right? So the message is going to be the previous representation, and that thing will be scaled by just a degree, right, of that node over here. Okay, so the aggregation function, it will truly be a summation, right? So that's why sometimes we call it an aggregation function, right? And then what happens is we take that aggregated message, right, and then essentially we have the multiplied by weight matrix, right? And you apply a nonlinear, activation function to give me the new representation of the node. So it's like the updated representation. Okay. Now, if you notice over here, that function over here does not take into account the representation of the node itself. Okay. Now, if I want that thing to take into account the representation of the node itself in that formalism, I'll just put a self loop over here to do that. Actually, I'm taking it back. So that thing is already here. So the self loop is on that summation over here, union V. Okay. So this is the simplest network I can have. Neural network I have is a graph convolution network, right? And usually phi is like a element-wise ReLU function. Another very commonly used network that I have is like a refinement over the GCN. But the key difference is I use attention to, instead of doing just a kind of just a simple summation of the incoming messages, I do a weighted summation of the incoming messages based on an attention weight that I compute, right? And other than that, the model is similar to that before. And another example of a very commonly used GNN is the relational graph convolution network. And the idea for the use case of that network is for problems in which the underlying network is heterogeneous. So by heterogeneous over here, we're talking about networks in which the entities, right, are connected via different relation types, right? And also have entities of different types. So this is the case, for example, of some sort of a people network over here that says, that guy over here, Mikhail Baryshnikov, was educated in Vaganova Academy, just sits in the USA, and was awarded the Vilsack Prize, right? So in this particular case, the edges over here correspond to different relation types, right? And the nodes tend to be of different type, right? So it's like a sort of, this is like a country type of nodes. This is a ballet dancer. This is an award in the university. Okay. So in the IGCN, what happens is instead of treating those edges, the same way, irrespective of which relation they are, I do essentially an aggregation, right, on a per relation type. Okay, so for instance, if I have a bunch of different relations, right, and connecting to a particular node, right, then I first do essentially a GCN for each relation, right, and then aggregate those to give me the final thing. Okay, so conceptually, I have a per relation weight matrix, right? That I aggregate, so the WR is a pair relation. Think of them as a message. Is a message function, right? And then the messages that I send, and I aggregate them, right? And then I pass them through again a nonlinear activation function with a weight matrix to do the update. Okay, so now, so there are. So in terms of, I already mentioned the whole idea of an end-to-end training, right? And the way that end-to-end training is done in a GNN is and I'll give you guys a very simple example, is and again, running out of time. Okay, so here's like give an example for a graph classification. This is something we haven't talked about, right? So in the graph classification, if you guys remember, the task is to be able to classify an entire graph, right? So far, the only thing that we talked about was how to compute a representation for a particular node. Now, the way I will use a graph neural network to do a graph classification is I compute representations for all the nodes in my graph, right? So this is a H sub 1 superscript L all the way up to H sub n superscript L. Those are the outputs of a L layer graph neural network for each one of my vertices, right? Then I have a function that combines those representations to give me a single representation of a graph. This is usually referred to as a readout function, right? And then I usually tend to, if I want to solve a classification problem, then I define typically I define a cross entropy loss, right? By passing it through a dense layer and the label and the ground truth label, right? So once I have something like that, right, then I have I have the graph. I have my GNN over here to give me a representation of the nodes. I have all those nodes representation coming out of the GNN, right? They give me a readout, representation of the entire graph, right? I then pass it through a dense layer and give me a classification, right? And based on the loss, I go essentially back propagate back, both in the weights on the dense layer, as well as all the way to, on the representations and all the way down over here to the GNN model parameters, right? So in this way, I can train in an end-to-end fashion, the parameters of my GNN so that, when I, aggregate them via a readout and pass them to a dense classification layer, then I will get the correct prediction. So, so quite often, the domains for which I would like to run my GNNs, involve graphs that are extremely large, right? Typical cases, and by large, we're talking about domains with millions of nodes and billions of edges. Think of applications in social networks, recommendations, knowledge graphs, and so forth. Okay, and it's important to be able to actually train the GNNs in a scalable way. So the way that scalability is achieved is usually via mini batch training. And the way mini batch training works is that, so remember, in the context of especially an inductive GNN, right? A GNN in which, I would like to estimate just the function that will give me a representation of a node, right? What I can do is I can pick up a node over here, which is, let's say my target node, right? And I can look at its ego network, right? And I'm going to have essentially a pictorial representation in the form of a tree in terms of how messages will propagate from the lower layer or on the GNN all the way to the top layer of the GNN. So this is the computational graph associated, right, with that particular estimating the representation of node 1. Okay, so then I can form a mini batch, right, by sampling a small number of those nodes, putting everything together, and that creates a kind of a small computation that I can go ahead and actually, potentially do it really fast by, moving the data on a GPU. However, quite often what is happening is because of most real world problems tend to have involve small world graphs, right? Or another way, some of the nodes, it's a parallel distribution of the nodes, and quite often the computational graph, right, after one or two layers in the GNN, will explode to actually include a very large number of nodes, right? So creating mini batches in this way, is not actually computationally very feasible. And in order to tackle that, what people tend to do is tend to actually prune the computational graph by employing a bunch of different sampling techniques, right? So for instance, if I have a computational graph like that, usually, a common way of doing that is to do one neighbor sampling, right? And the neighbor sampling can be, the simplest one where you say that, you limit the number of neighbors. So, you fix the number of neighbors that you can have at each level, right? To at most, let's say, a constant number. and you select those things randomly, right? So this is a case in which, I set the number of neighbors to at most 2, right? For one, I sampled 2 and 4, right? And then 2 has only one neighbor, so I would just keep it. 4 has a bunch of neighbors, so I would randomly sample 2 of them, which is 7 and 8, right? So that computational graph now becomes that small computational graph over here. And I can create a mini batch consisting many of such target nodes, and then leads to a problem that is computationally trackable. Okay? So to conclude, right? So there are many applications that can be solved by formulated machine learning on graph problems, right? So graph neural networks are a new technique for graph learning, and have become very popular in recent years, and they have multiple advantages over traditional approaches. And then GNNs can be used for a variety of tasks, right? And actually can be trained efficiently on very large graphs. And I'll stop here and open it up for questions.
Yeah, so if there are no questions, I can ask a quick one. This is Puya.
Hey, Puya.
Hi. So one thing I noticed is, probably it's a small thing, is that when you did the representation of the graph, there was as an income, as an input, just the age that was going from let's say the node to the neighbors, and not from the neighbors to the nodes. I don't know if you can pull that back, like E, B.
You're talking about over here?
No, just even one before. Even one before.
Over here.
So from V to W. So if you look at the last page, you can see that it's going from the node to the neighbors, right?
Oh. Bless you.
That's you.
So.
Is it?
Like, you mean I think that this is over here. That's a typo. That's what you're talking about, right?
Oh yeah. So that's like W to
V. Yeah. So it should be WV. Sorry.
Yeah, no problem.
Good catch.
Nice.
Good catch. That real-time correction, right?
Yeah, great. Thanks for the tutorial. So far, it's very good.
Thank you. Any other questions? Okay, so if you guys don't have any questions, then I'll let Zizi, continue after that. And again, if you guys, have any questions, and you're shy to ask, right, you can always put them on the chat or send me an email directly, and I'll be happy to answer them.
All right. Let me try bring up the. Hello, guys. Can you hear me all right?
Yep.
Yes, Zizi.
Okay. You see the my screen, right? Okay. Yep. All right. So that's the same page that George talked about earlier. If you want to, do the tutorial, send an email. All right. Okay. Okay. So just a little bit introduction of myself. Like George, I'm taking a leave of absence from NYU Shanghai, and I'm now part of AWS. I'm leading the AI lab in Shanghai. Right. So what I'm going to do is to give you a little bit history and the background, and then talk about the APIs and what's new in the release so far. Right. Okay. So So graph neural nets has been around for a couple of years. Actually, has a even longer history. We didn't start very early. We started spring of 2018, and the full development kicked off early summer. And in Europe's 18, we made the first release. So what I want to say is, after that, we have been making very rapid release every 3 months on average. Make a release to the public. And so 0.4 is, I think, in last New Year's. And just a couple of weeks ago, we released 0.43 with 3 major features. What is interesting is just a year after we released in Europe, we made it a managed service in AWS SageMaker. So we actually have active customers using DGLs, right? So that's a basic timelines, how things have happened. Let me start with the DGL meta objectives, and also a very quick look at the architecture. There are really 2 top level objectives. The first is to be forward and backward compatible. So what I mean by forward compatible, meaning essentially you want to make sure that it's easy for other people's researchers to develop new models. What do I mean by backwards? Is that we are conscious that although deep graph neural nets is a very good technology, in the end-to-end application, it's likely only part of your model. So for instance, if the graph is taking a paragraph of text as inputs, or it can take an image as input, then we're talking about feeding into a network some kind of representations. Now, if you want to train the model end to end, you might think of in the future, backpropagate the error all the way back to the feature extraction of the input. Likewise, if you think about, George talked about, for the graph, you usually have link predictions and node classification, graph readouts, but you can think of also scenarios where you have a knowledge graph represents what you want to say. Yeah. And then you have a LSTM following that to decode a sentence that describes your knowledge graph. So in both of these cases, we are seeing, a reason to have, a DGL itself platform agnostic, because those other modules you may have chosen to implement them in other frameworks such as MixNet, PyTorch, TensorFlow, or whatnot. Right? So that's a pretty big decision, because essentially we're supporting many different deep learning frameworks. So if you look at the architecture on the right, we have multiple backends. We started out with MixNet, and then soon we realized we need to support PyTorch. And at the very top is the key data structures DGL users use: the graphs, message passing APIs, operations on graphs, and then following that, there are data flow graph schedulers and our own TensorFlow operations and so on, operators and so on. So that gives you a bird's eye view of the architecture. The second thing is easy to understand. We want to make it really fast and scalable. Right. So how do we design the APIs? So very importantly, we realize that we need to handle message propagations in a variety of different ways. So the one that George talked about earlier is probably the most popular ones. For anybody to come to GN, you think of, essentially you're just sending messages to your neighbors, wrongs after wrongs. So everyone shouts to everyone near you. Right? That's a full propagation. But another scenario, another pattern that is very important is to propagate your message according to some graph, traversal orders. let's say you want to encode a sentence, depending on its path trees, you're aggregating messages, up the levels. Brief propagation, the same thing. And George talked about earlier that is doing sampling. Essentially, you have a node that's pulling, representing from its neighbors, some selected neighbors, and so on and so forth. In this way, you're really looking at an eco network, and you're propagating the message up to your root nodes. Of course, you can do random walk and so on and so forth. So there's a need to control how we let the message propagate. Did I? So I think I missed a. Sorry, hold on a sec. Missed. So let me do that again.
I think what you want to do is to remove the ZZ audio, and you can do it if you're the host.
Yeah, sorry, I'm back. Sorry about this. And then the second thing, once we control the message, we know there is a need to control the message propagation. There is a need to do the second thing is to do the, what we do when the messages are propagating. So marrying the deep learning with message passing means that we have parameterized, nonlinear transformation embedded when we sending the messages. So the parameters here are the networks that neural networks that process the messages, taking inputs from the two representations on the end to endpoints, and also on the edge as well, right? Then when the messages arise, sorry, how come? All right, so here. So when that message arises, you need to aggregate them. That's the reduce functions. Once you have that summary of the messages from your neighbors, then you apply another nonlinear transformation to aggregate with its previous representation. So there are three message functions. So there are three message handlings when it's message functions, the reduce functions, and update functions. So for now, there is, you could do some very simple aggregations, very simple message passing functions, but to enable that further research on that, we need to make them customizable. So in DGL, there is just one central abstraction, DGL graph, and we have syntactic triggers for you to access the data on your graph. So gn.n data is to access a field called edge on any of the node data, and then you can have g.e data and so on and so forth. Right? That's essentially there's a bunch of abstractions to help you to access the data itself. Now, remember I talked about earlier, we have to do the two things. One is to handle the messages when they arrive. The other is to control the message propagations. So what we do is we decide to generalize two key APIs that is familiar for, I guess, so for LO computer science people, which is, think of a socket, right? You have send and receive. So the extension here is what we call the active set. So active set is essentially a set of edges where you apply a message transformation functions on. Now, when the messages arrived, we have another set. That's the active set is the vertices, which takes the messages and apply reduce functions and the update functions. So all those functions, the three functions are user-defined functions, can be user-defined functions, but also we have built-in functions to make it faster. And the different propagations are just handled by different update rules. So let's take some examples here. So in the basic GNNs, you are aggregating messages from all your neighbors without doing any transformations. And when you do the reduction, you might take a max, you might take a mean. And the API here called update all is essentially a shortcut saying that all the edges in the network, all the nodes in the network are the active sets. So if you see here, it takes, just copy, so the message function just essentially copy the source representation to a field called M that is a mailbox. And then when you do the reduction, it takes max. Similar for when you do the mean, you just use this function. So a more complex network is GAT, stands for Graph Attentional Neural Nets. Essentially, what it does is to impose a weighted sum of your neighbors. And the weight is computed according to the similarity of the two nodes representations. So for this, you can write your own message functions and reduce functions. In our implementation, there's some typo here. In this implementation, what we do, we send the original representation from source node along with a normalized similarity, so a normalized weight here. And when you do the reduce functions, we normalize that, and then we do a dot product, and that is it. So you can see it's very flexible to implement things like a GAT. Right? Now, what I described is the core of DGL, essentially handling the messages and process the messages. But we soon realized that we are dealing with many different scenarios. For instance, you can have a social network that is really, really big, right? It's what we call a single giant graph. What we need to do is you need to do samplings. Now, if we do drug discoveries, if we process a lot of natural language sentences, we're dealing with many small, moderated or to moderate size graphs, which means we need to batch graphs. And for drug discoveries, we need to dynamically modify the graphs. The topology itself means that we need to add edges, needed to add nodes for generating models. So we need to have mutation APIs. Another thing that George talked about earlier is that in real-world networks, there are a lot of different types of nodes, a lot of different types of edges, therefore need to support heterogeneous graphs. So in terms of functionalities, we're breaking down DGL APIs into certain groups. We have the message passing functions. We can support arbitrary message functions, arbitrary reduce functions, arbitrary update functions, right? Although everything is built on top of the send receive kind of abstractions. And with different ways to control how the message propagates in the network. The for propagation and sampling one probably the most popular. The key actually here is active set, although programmers don't see that. And then we have batch APIs dealing with many and small graphs, sampling for giant graphs, generated models supported by mutations, and heterogeneous graphs. And again, we support multiple platforms. I don't think there are any other frameworks that support that. Okay, how does it work? First release, we saw we did pretty well. That's the reason being, those graphs are really small. So we thought we were doing pretty well, but then the PyG came along, and as you can see that, oops, PyG is sometimes much faster than us. So what is the problem here, right? The problem is because we're supporting multiple backend, at that time we thought we would just handle all the sparse operators by the backends themselves, and we soon realized that this is not a good idea because some of the key operators, for instance PyTorch and Mixed-Dat, they have different optimizations and they're not doing very well. So that's why we started to hack into the code such that we have custom OP plugins, and we do our own custom kernels. And the result, as you can see here, that we're essentially neck to neck in terms of performance. What is more, DGL is very memory efficient. We can train the full Reddit on the 16 gigabytes GPU, whereas PyTorch geometric PyG actually ran out of memory. It can be run if we reduce Reddit data set, but then still we're almost 3 times faster and consumes like a 5 times, so 1/5 of the memory of PyG. Now that's the performance on small networks. Let's look at, for instance, how DGL works on single machine with single GPU. We can push the performance pretty well, either by increasing the nodes. The other experiment we did is keep the network the same, but we add make the network more denser. You can see that DGL scales pretty well here. That's on single machine, single GPU. On single machines, we can have multiple GPUs and improve the paradigms. As you can see, that's a typical kind of sublinear increase of the performance on multiple GPUs. There's comparison if you do run it on the NUMA machine. As you can see, GPU is quite faster. So if we run on a single machine with multiple cores on that single machine NUMA machine, if we run it out of the box, as you can see, we're not doing any optimization. It's that the performance is very close to, even just a one NUMA node. But with 4 NUMA modes and turn up the NUMA aware optimization, you can see essentially we have very good speed up, right? Again, so like I talked about earlier, that auto batching is important for quite a few different data sets for mini batch, for giant graphs, or for drug discovery, where you have many different kind of molecules. And you can see the performance is well, as this is on training on 3L10. Okay, so I'm going to quickly talk through some of the new features we have in 0.4 and 0.43 releases. In 0.4 releases, we support heterogeneous graphs. So here is an example that we're doing recommender systems. You have books, and for instance, the users may like some books or read some books or dislike something. So nodes and edges are different. They have different types of nodes and edges. And here in this, the GCMC stands for Graph Convolution Matches Completion. It uses a graph autoencoder and decoder to do the link predictions. So what we did is we realized that we need to have per type weight matrices, and then what we need to do is to extend the API so that we can aggregate the messages according to different types, and we should do the reduction according to different type of messages. Right? So the extension is just called multi-update all. That is extension to a heterogeneous graph. How does it work? For GCMC, you can see that we have very good speed up when we scale the data sets. For movie length 1 million, we are like 20 times more faster than the official implementation. What I mean by this is, of course, you can implement a heterogeneous graph neural nets by yourself, but by baking the support in DGL, we can do a much better job here. For 10 million, movie length 10 million, the other it takes like one epoch will take like for a much longer time than DGL's version. Another example is drug discovery. So there is I'm not going to talk about the details of this model, but this model needs to use heterogeneous APIs. Essentially, the atoms in the drugs have different bonds, and then we can use heterograph to support that. You can see we can easily get almost more than 4 times speed up. Just a slight digress. So drug discovery is one of the application domain that we focus very early on. There are generative models, there's other property prediction models that's also possible. Across board, we're seeing very good speed ups. Now, 0.43 that release, which we announced about 2 weeks back, is a minor release, but with a lot of important features. One of them is TensorFlow backend. The other that we did is we realized, in addition to just supporting the message passing group graph neural networks, the core APIs, the core packages, we see a lot of adoptions and needs in different kind of domains. One of them is knowledge graph embeddings. The other is life science. We played with them a little bit early on, but now we are formally announcing a separate domain package for them. I'm not going to talk about DGL life science too much, except to note that we are now doubling. Essentially, we have 10 models for life science for drug discoveries. And the last thing that is very important is we're making a step towards supporting the giant graphs by announcing sampling APIs. Now with TensorFlow backend, we can now truly claim to be platform agnostic. Now we support PyTorch, MixNet, and TensorFlow. And with that release, we have 15 most common GM modules. And on average, if you look at the comparison against other TensorFlow graph neural nets frameworks, we are like 3 times 5 faster than GraphNet. They're almost 2 times faster than TensorFlow geometric. If you are using PyTorch, you are in luck because PyTorch version is still faster than the TensorFlow. The reason has to do with some inefficient support with the TensorFlow stack itself. So this is a very important announcement because a lot of industrial users are using TensorFlow. Second thing, the DGL knowledge graph embedding. This is a very important domain. I think is very keen for www conference users, researchers, because you use those knowledge graph embeddings for many downstream tasks. Now, here we compare with PyTorch Big Graph. So you can see this is we are training on the 4 freebase data set. When we run on 4 machines, we support distributed trainings. When we run on 4 NUMA machines, you can see we can complete the whole data set training in 30 minutes. Right? All right. So the knowledge graph for those models, like say Trans-C families, Trans-X families, you don't really use graph neural nets, right? You're comparing, you're computing essentially a pair of nodes to compute the similarity and so on and so forth. But the DGL underlying storage optimization really help us to get good performance. This is one of the key reasons that we are faster than PyTorch Big Graph. And it runs on multi-GPU as well, right? So there's another very cool packages, Graphite. You can see that we are, again, quite a bit faster than that. Within it, you notice that on 1 GPU, we're faster than Graphite. That's one thing to notice. The other thing is the Graphite use C++ API to implement the different models. So that is more difficult to do. And in DGL-KE, we essentially use Python to write the models. Even with that, you can see that we are far better than Graphite. So we're very happy to announce this DGL-KE. So sampling. Sampling is a very important, I think it's still evolving, dynamically evolving research field. So in this release, we support some rudimentary neighbor samplings. And to reduce variance, there's an important optimization called control variate, which subtract dynamically tracked baselines. So we support that as well, and we also support random walk. What is important here is that this works off the bat with many gens, wherever you can use a simple neighbor sampling on. Again, realize the need that we can, people want to experiment with different kind of sampling algorithms. We support customizable sampling APIs. Also, we support heterogeneous graph because heterogeneous graph is released already in 0.4, and we see that it's important. Gen graphs also have very often heterographs as well. So we did a very good job to make sure it's backward compatible, that all the LM modules that we have already announced can be used without changes. And again, we use, we do aggressive engineering, use multi-processing and multi-threading for performance improvement. Right. So we are going to announce a preview of distributed training of GCN Gen very soon, and we're working very hard on this. So 0.5 is exclusively focused on doing distributed training. Right. So we've been focusing from those graphs for recommender system for detections and knowledge graphs, so on and so forth. But this is just only part of the total picture. Now, those are graphs are very, very big, but there are only very few of them in the world. But if you think of there is a knowledge embedded in any sentence that I'm speaking, so you can think of there's a graph that for a sentence that people generate every second. Also in the images, you can think of them, there is a relationship among the objects within the images. So I think graph is key to solve the strong AI problem in the future. What we need to do is to make sure there is a way to marry these two type of graphs. So I'm going to talk just very briefly. It's just extending the picture we had earlier to set several examples that I see for natural language processing field. For instance, transformer. People understand transformers. They typically think of transformers as a stacks of linear transformations, nonlinear transformations across all the tokens in the sentences, and doing normalization and so on and so forth. But this is really a graph attention network followed by some residual connections. So you can see transformer, which kind of revolutionized LLP field as a graph neural net, except it's on the foregraph. So transformer essentially are doing, it is essentially a complete graph. So that's why it needs a lot of data to train. So if you look at this from the graph perspective, then you can think of some other cool optimizations. So instead of, for instance, instead of sending messages to every other nodes, you can aggregate them to a central node and disseminate, right? So in this case, the graph is much sparser, right? So that reduces complexity to out of n. So you can train on the smaller data set. And of course, you can do some other fancy algorithm, fancy optimization, make it auto n log n. So that's one example. Another example I mentioned, kind of briefly touched upon earlier for graph nets. Let's say you want to generate a text according to some graphs, right? In this case, you have a paper abstract here, which is really talking about some cool work some people does, right? So that's a very small knowledge graph. So what you want to do is to encode this graph, and then you decode it into a text. So again, what you do is you have graph attention networks here, kind of summarize the graph, and the LSTM is to attend to the graph nodes and generates sentences, right? It either copies the token or produce a new ones. Okay, so that's a very interesting model. I think it's pretty fundamental for natural language processing. So there's official versions, and there's one that we implement in DGL. You can see that we're almost 2 times better. I think the graphs in NLP fields are still kind of nascent and ongoing. There are a lot of interest and to do those kind of researches. So another scenario that is very important goes to the fundamental questions about how we understand an image. So image is worth 1,000 words, but really there are, if you think of the objects, right? So there's something called a scene graph. What essentially you wanted to do in this task is to figure out the relationship among the objects. Right? You want to extract not only the objects, but also the relationship among the objects. So that is a step towards understanding the image in its essence. So implemented in DGL, where essentially at least like 3 times faster, right? So DGL itself is open source, right? So I'm just going to quickly give you a statistics updates. Less than 5 months ago, sorry, in New Reps, and this is the numbers we have today. We're adding more than 1,000 GitHub stars, 5-fold downloads, and so on and so forth. And of course, we are very keen on engaging open source communities. We'd really love to have you guys involved. So our next steps is DGL.5. I hope we can release that in about 2 months. We'll focus on distributed training. And I already hinted that we're planning on producing more domain packages of DGL. All right. So I think I'm done. I probably went too quickly actually. So if you use DGL, please sign our paper. We're going to write an updated overview of DGL, and so the essence of our research in Shanghai lab, you want to leverage graph when it's available, and otherwise we discover the graph. That's like 2 sides of the same coin. And also we are hiring, so I think that's it. So I will take questions. Sorry, I still need to share screen. Right. Okay.
Right. If there are no questions, I can ask you, can you go to slide number 9 or 10 and maybe walk us, I know that we will see it later, but line by line the code, like it's a hello world, no? So I just want to, if we have time, just like either 9 or 10 and just go line by line this hello world.
Oh, okay. Yeah, all right. So can you see the screen now?
Yes, thanks.
Okay, so this is, as I mentioned earlier, so the real plugin is this, that is you want to figure out the active sets of the edges, active sets of the vertices, but this is not what we expose to the end users. But remember, so end user needs to plug in, remember 2 things, is what is your update patterns are, what is your message function patterns are, and then you plug in the message function, reduce function, and so on and so forth. Now, bear this in mind. Now in this, in the 3rd line here, update all essentially means your update patterns is you're sending message to all your neighbors. So every node is going to receive messages from its neighbors, and that is update patterns. So update all is syntactic sugar saying we're having 4 updates. Now you plug in the message functions. The message function is like copy U, that is U, and we essentially use U and V as a pair. So U is saying that I'm going to copy the update. So gn.data h. So this is the input, the features, right? So we are setting the older node, their hidden layers with the name in the edge with this feature. So this the second line essentially sets the input features, and then you are doing the propagations. So the message function simply says I'm going to copy over, because here is essentially we're doing this. I think we actually made a mistake. There should be a sigma. I'm sorry. So there should be a sigma here, right? So we essentially copy a message from neighbors, and the aggregations in the reduce function we are using a max function, max, right? Similarly, we do copy for the mean aggregation. We are taking mean for the reduction, right? And after this, you're done. Then you have like the final layer HN. This is your this is essentially the final representations. So in this particular example, we're doing graph graph classification. So we're concatenating everything, right? And then we do a riddle to compute a final representation and use this to do to classify whether this drug has this property or that properties. I think GAT is a little bit involved. I'd rather wait for the Ming J and other people to talk about for that. Is that okay?
Yeah, it was clear. Yeah, thanks.
All right. Any other questions? If no, I guess that's for coffee breaks. And again, you can send us emails, messages, so we'd love to hear from you and talk to you. Yeah.
Yeah, it will be a 30 minutes break. And we will start the hands-on part at 11 a.m., I suppose. Yes, 11 a.m.
All right, so I'll stop the sharing.
Let me get... Oh, okay. Let's get it going. So hello everyone. Welcome to this tutorial, the learning graph neural networks with DGL. So this is the hands-on tutorial part. So you are expected to see some real code or even play with it. So again, for people who wanted to try that out, please send an email to this email address, and you will receive 2 emails and click the notebook link in the second one. We already set up a service. So you just click that and all the environments have been configured. So you don't need to worry about anything. So the startup time is approximately 10 minutes. So just be a little bit patient. And if you have any questions, so you can join our Slack channel or just post questions in the chat so people can answer that. All right, so let's start it. So the hands-on session, we have actually 3 sessions. In the morning session, we'll talk about using GNNs for basic graph tasks. So it will be done by me. And it's each session is roughly an hour and 30 minutes. And in the afternoon, we'll cover more advanced topics, like training on large graphs by DAR. You will understand, okay, if your graph is large, like have millions or billions of nodes, how to do it in DGL. And our last session is about using GNNs for real world applications like recommended systems and fraud detections. Okay, so my session is about GNNs for basic graph tasks. Okay, so the word basic means that word starts from something simple. Okay, I know you guys. A lot of you guys are actually data scientists or have the experience of working with data. So suppose you now have a graph data. So okay, what do you will do with it? You'll probably think about, okay, I have a graph data stored on in some format on disk. I will try to load it into memory, pre-process it, and prepare training and testing sets. For example, if I wanted to perform some machine learning task on it. And later, you will build a machine learning model to finish some particular tasks. And because we are talking about graph neural network, we would like to see how to build and train such a model, such kinds of model. And when we build and train these models, we can optimize these models for many different goals. And in graph domain, we can particularly divide these goals into 3 categories. The first one is called node classification, where we try to predict some labels of each node. So one example is community detection. We wanted to predict, okay, whether this user is from this committee or another one. So it's typically a node classification task. Another very common task is link prediction. For example, in the later session, we'll talk about the recommender systems, and you will see that on a user and item a linkage graph, to predict, okay, whether the user will purchase another good is equivalent to actually to perform a link prediction task on graph. And finally, we have graph classification, where we want to get a label, basically predict a label of the whole graph structure, which is very common in bioinformatics and chemical domain. Sometimes, for example, given a molecule, which is a structure, you wanted to predict, okay, what are the properties of that particular structure, and give a label of that. So these are typically graph classification tasks. So you can see this is a typical workflow where you have a graph data and you wanted to perform train a machine learning model and to finish some task. And in my session, we actually have several notebooks to guide through several stages of this pipeline. So first, we'll have this one load data notebook. It will cover how we load a graph from a particular format on disk, and how we pre-process the structure, do some query, and also preparing the training and testing like a data split. And then later, we have another notebook to talk about the graph neural network, how we build a graph neural network model in DGL to finish a node classification task, which in this case is for community detection. And then in the third part, we actually reused the same GN model to perform a link prediction task on the same data set. So the idea here is to show you guys that the GNN is a powerful tool that can be used in different tasks, and you can just change a little bit of code and you can use it in different pipelines. And for all these small sessions, we are using this data called Zachary's Karate Club network. So what is a Zachary's Karate Club network? So it has a very interesting story behind it. So the Karate Club, it has like 34 members. It is like a social network studied from approximately the 1970s. And it has 34 members. And you can see on your left-hand side, this is the graph, have 34 nodes. Each node is a member. And it also documents the links between between a pair of nodes, where it represents how these members interact with each other outside the club. So you can think about this as a social network. So so later, unfortunately, as the times goes by, tensions grows as well between these members. So eventually, this club actually splits into two committees, one led by the instructor and the other led by the president of this club. And you can see on your right-hand side, this is the color means, okay, which member goes to which community. And this is why this network is so interesting, because it's a real case for community detection. And people have been playing with this for a long time, like try to understand whether we can derive this community membership by looking at the graph structure itself. And in our tutorial, we'll actually talk about how we achieve this community detection using a graph neural network. So, okay, so you can see we will have 4 notebooks, and the 3 of them have introduced 3 of them. And if time is allowed, I will also talk a little bit about the message passing interface that is useful for customize a GM module. So, yes, I suppose you guys have already received the email, and if you did, you can click the link, and you should be able to open up a Jupyter notebook, and you can click the www the folder, and you can see this structure. And our notebooks are all here in the basics task. So click this one. You can see, okay, there are 4 Jupyter notebooks here. And let's start it with the first one, load data. So let's click this. Okay. All right. So for people who are not familiar with Jupyter Notebook, so the notebook contains a lot of cells, and each cell has codes, and you can always like run the cell using this run commands, or using Shift and Enter. And if you mess something error, for example, you mistype something, and it has some errors, you can always click this kernel and restart and run all. So you can all restart clear output to start over again. Okay. So this session, I will talk about how to load the Zachary Karate Club network. I've talked about it before, and we will talk about how we load that data into GGL construct a graph, query some structural information, and also look at how we prepare these node and edge features. Okay, so we know that graphs are relations, right? So there are many ways to store a relational data. And one of the very common way to do that is using this comma separated value, CSV format. So in this tutorial, we also use that format as a starting point. And we have prepared 2 CSV files that store the Zachary's Karate Club network. So if we run, for example, we run this cell, it basically, you can see under the data folder, there are 2 CSV files, the nodes.csv and edges.csv. So the nodes.csv stores basically every club members and their attributes, and the edges.csv stores the pairwise interactions between 2 club members. So let's take a look at how these CSVs look like. Let's use pandas, a very classical tool to visualize and process tabular data. We can use pandas to load these CSV files just using this read CSV command. So you can see here when we load this tabular data and print it out, you can see there are 3 columns. The ID is basically the ID of each member, and the club is a string attribute, has 2 values, Mr. Hi and officer. So it is basically telling you that, okay, which member goes to whose community after the split. So there are 2 people here, Mr. Hi for the instructor and officer for basically the club president. And a third column called age is basically some extra information about these members, and age here is basically integer number for, okay, how old are they? All right, so we can also do the same thing for the address.csv. We load it, and we can visualize the data, and you can see, okay, there are 3 columns. the first two are source and the destination columns, meaning okay, between whom this particular interaction actually happens. So for example, the first interaction happens between the first member of this club, member 0, and the second one. And there's another like a column called weight, which measures the strength of this interaction. Like, okay, how close are they? Whether this interaction is like is a more friendly one or not. Okay, so now we have these tabular data. We need to think about, okay, how to construct a graph out of it, right? And in DGL, nodes are consecutive integers from 0. And this is why when we're preparing the data, we need to make sure that, okay, all the nodes in the table of data are actually correctly aligned. In this example, we have already like done that, because you can see that the IDs are starting from 0 to like to 33. So we have like 34 members here. The IDs are already consecutive integers from 0, so we don't need to do anything. But in the real scenario, if you have like different data, you might want to just first make sure that, okay, the first row corresponding to the the first row corresponding to node 0 in your graph, and it's also this attribute also is aligned, and also make sure that the edges has the correct node IDs. So okay, so to load this data into DGL to create a graph, you can see this is the code to do that. It's very simple. We just pick the source and destination columns from the address table. We convert it into NumPy arrays. Now we have 2 arrays, source and dest. And we create a DGL graph from a pair of NumPy arrays, and we can print it out. So you can see, well, first it prompts out that, okay, you are using backend, PyTorch backend right now, and in DGL you can switch to, for example, TensorFlow or MXNet backend very easily. And now we have a graph object. The graph has 34 nodes as we expected, and also 150 edges. And the N data schemes and the E data schemes are something about the feature attributes, where you see that later. But until now, everything looks pretty fine. But we wanted to have something more vivid. Now we want to see how the graph looks like. And to visualize it, we can convert a DGL graph to a NetworkX graph. So NetworkX is another popular Python package out there for people to analyze graph structures or do visualizations. And in DGL, you can use this g.toNetworkX function to convert this graph to NetworkX. And you can print it out and visualize it using NetworkX very easily. So we run this code. And it takes a while, but yeah, it finally get the visualization. You can see all the nodes and their labels and their connections between them. Okay. So, okay, so far so good. And we know that when we have a graph, we also wanted to not only visualize it, we also wanted to do some like queries. So what I mean by querying is I wanted to know, okay, for each node, for example, what are the nodes it connects to, right? So to do that, DGL has a lot of APIs for you to like achieve this functionality. So first of all, for example, instead of just print this graph to get these meta informations, you can also use this g.number of nodes and g.number of edges to get the number of nodes and edges in this graph. So we can run this, and you can see, okay, there's number of nodes and number of edges. You can also perform queries on graph structures, like get the in degree of node 0, and we can run this. You can see there are 16 nodes, right? 16 nodes, like there's node 0. I don't want to count that, but it's correct. And you can also get all the nodes that node 0 connects to. So we call this g.successor 0, and you'll get a tensor. So this tensor is essentially a PyTorch tensor. So that's why you can use it for example, in other tasks, in other like computation with PyTorch tensor, and you can see the contents are basically the node IDs in the graph. And in DGL, we have a bunch of these kind of APIs called query APIs, and you can see the full API document here. And this is just a screenshot of all these APIs. And you can see you can query the predecessors, successors, in and out the edges, so on and so forth, for different kind of purposes. Okay, so these are the graph structures. Now we need to talk about the node and the edge features. So we know that in real world, right? Like when we have a graph, we also will have attributes. And the one powerful thing about the graph neural network is that it can take care of both graph structure and the node and edge features. So we need to formulate, we need to actually get that from the data. In this CSV, if you look at it, you can see, okay, the node and the edge attributes can be arbitrary, right? You can have a string type, you can have integer type, you can also have floating value type, right? But in DGL, we only accept attributes stored in tensors. And this is because like DGL is a package for graph neural network for deep learning, right? And deep learning, we work with a lot of tensors and vectors. In most cases, we are dealing with numerical values. So that's why we have this restriction. And another reason why we think this is a fair assumption is that the development of deep learning has provided us many ways to vectorize the various attributes into numerical features. And we have some like general high-level suggestions here. For example, you will have, for example, a categorical attributes like a gender or the occupation of a person, and you can consider converting them to integers or one-hot encoding. So yeah, it basically a typical way to doing that. And for verbal and string contents like an article, a document, or quote from someone, you can use a language model to do that, like LSTM or recurrent or other recurrent neural network, or like a BERT or transformer models to encode that sentences or like a sequence into verbal and sequences into fixed length vectors. And for images, you can imagine that you can apply a vision model like CNNs. So for this particular data set, we have actually the following attribute columns. So we have the age of each member, which is already an integer attribute. And the club is a categorical string attribute representing which community each member belongs to. And the weight is a floating number again, so it's still it's again a numerical value indicating the strength of each interaction. So okay, let's see how we handle these different attributes and put it into DGL. So suppose, okay, for we are using touch, so you can import touch here, and for the age attributes, it's already integer, so we can load it just using this. We can get it out of the pandas data frame using the age like name, convert it into PyTorch tensor, and it is possible that we wanted to normalize it into some range that is more friendly to the training process. So we convert into a floating tensor and divide it by 100, and you can see basically this is how the feature looks like, right? So you can see it's between 0 and 1, and remember. When we get the features, feature columns out there, so it is aligned with the nodes. So for example, the first element of this array will correspond to the age of the first member, so on and so forth. So that's why when we try to get a particular member's feature, we can just use this tensor slice operations to do that. And this is how we get the features of node 0 and node 10. We can run this, and you can see I get the like their age, the normalized feature. And after that, we can save that feature to DGL using this g.n data dictionary. So the g.n data syntax. So g.n data is like a dictionary. You can you can assign this feature to our graph under some name. So I give it age here, and we can run this, and you can see that when we print out the graph right now, the N data schemes now have actually more stuff here. So you have the name of this feature, and you also have the shape. The shape, because for each member, the feature is just a scalar, so that's why its feature shape is empty, and the data type is float32. Okay, so let's look at the club feature. So remember, the club feature is a string. It has Mr. Hi and officer, right? So when you convert it into integer or one-hot encoding for these kind of categorical features. So this is how we do it. We first get this like column out of data frame and convert it into a list. And then we'll convert it into a PyTorch tensor with 0, 1, 0 for Mr. Hi and 1 for officer. And we can also convert it into a one-hot encoding. So you can use PyTorch's one-hot function to convert it into one-hot encoding, and then we can print it out. So let's run this code, and you can see when we print out this one-hot encoding, it's either 0, 1 or 1, 0. And remember, I talked about the G.N data. It looks like a dictionary. It is in fact a dictionary, so you can use any normal dictionary operation on it. So here we use this update operation from Python dictionary to update, to save basically multiple node features into my graph by like specify a dictionary here. And we can also use delete to remove some unnecessary features from this graph, like the age, and I can print it out this graph again. And now you can see that, okay, the graph again has 34 nodes and 156 edges, and the N data schemes now has 2 members, right? One is the club. So again, it's a scalar feature, so the shape is 0, but the type is integer. And we have club 1 hot. So now the feature shape is a vector of length 2, and the size is, the data type is integer 64. So, okay, so quite straightforward. And we can also do that for edge features as well. So we have N data, so it's not hard to imagine we have E data as well. So here we assign basically the weight, right? The weight feature to the graph using this G.E data syntax. And we can print out the graph after we set the edge weight into graph. As you can see, the E data schemes now have weight as one of these features, edge features. Okay, so that's how we load. Then that's how we load the graph structure into DGL from a CSV format. Do some query, and also how we process the features. So, any questions so far? Cool. Okay, so now let's go to the second one, the GNN notebook. Let's click that. Okay, so this notebook is about a semi-supervised community detection task using graph neural networks. And as I have mentioned before, the Karate Club is a social network that has 34 members and their interactions. And the club is split later, led by the instructor, which is node 0 actually, and node 32, the club president. And you can see this is a visualization about the community and how it is split. And the goal in this session is to formulate this community detection problem as a semi-supervised node classification task. And we will build a very popular graph neural network model called Graph Sage, proposed by Hamilton. And we will train the model and try to understand the result. Okay, so let's first run this cell, which imports a bunch of packages. And now let's look at this community detection problem. So For people who have experience with graph data, you might know that the detecting community structure has been widely studied. Actually, there are many different ways to do that, like spectral clustering, k-means, or k-nearest neighbor, something like that. Yeah, and these methods are usually unsupervised, which means we only look at the graph connectivity and we try to predict the community labels. Recently, Thomas Keefe, who is also the author of graph convolution neural net, proposed to formulate this community detection problem as a semi-supervised node classification task. So what I mean by semi-supervised is that although the majority of the nodes are still unlabeled, we actually utilize a small portion of the node labels to give a teaching signal to the neural net. This amount of label nodes are particularly very small, usually very small, like 1%, 2%, very small amount. So the task is still relatively hard and also relatively realistic, because in the real world, you don't have many labels. And he showed that in such a setting, a GNN can actually accurately predict the community labels for those nodes that does not have, like, we don't use their labels. In this tutorial, we apply this idea. We apply Keefe setting to the Zaptrace Karate Club network to predict the community membership, where only a few nodes are used. Okay, so the first thing we need to do is to load the data and know the labels. And we have already covered that in the last session. So we provided you a function for doing that. So we can just run this cell. And you can see we loaded a graph, 34 nodes and 150 edges. All things are good. And you have the node data. So here we have two node data. One is the club, the 0, 1 labels of each node, and a one-hot label, which is like 0, 1, or 1, 0. Okay. So now we need to think about what are the node features, right? You can see that the clubs are labels, but what are the node features? In fact, in the original Zaptrace club graph, the graph is featureless, so there's no node feature at all. The age attributes you saw before is an artificial one I just actually added to the data set just for purpose of demonstration. So the graph, all the nodes do not have features in this graph. And how can we do that? Like a common practice to do that is to use an embedding weight that is updated during training for every node. And we can do that using PyTorch's embedding module. So here, this is how the code shows how we do that. We first using n.embedding and create an embedding tensor of size number of nodes and the length of the embedding to be 5. And we assign the embedding weight to the node as the inputs, just have another variable, and we initialize it properly. And we can print it out. You can see these are basically the initial node features for this graph neural net. And these are like common ways to do that when you're using embedding layers in PyTorch, for example. And as for the labels, remember our setting is semi-supervised classification, so only a small portion of the nodes are labeled. And in this example, we only label 2 nodes. One is the instructor node 0, and the other is the president node 33. And you can see how we get all the labels from the node.ndata club. So it's a 0, 1 label. And for the 0 and 32 nodes, their labels can be extracted by using a tensor slice operation. So something like that. And you can see, okay, one label is 0, another label is 1. Okay. Now we need to define GNN model. Okay, so a GNN model, in this example we use is GraphSage. So GraphSage is a very popular model, and its equations are like this. So remember in the previous slide, in the morning session, Zizi and George has been talking about the idea of message passing. So GraphSage is nothing different. You can see these 2 equations. The first equation basically gathers the neighbor representation HU from the last layer of a particular node V. It gathers all these neighbor representations and apply an aggregation function on it. The aggregation function can be customized, such as like average, sum, max, min, something like that. And afterwards, it concatenates its own representation from the last layer with the aggregated node representation, neighbor representations, and apply a fine transformation and a nonlinear activation function to get a new representation. And this is the formulation, the equations for one layer, and you can potentially stack these like layers multiple times to get a deeper neural network. And one interesting thing about graph neural network is that you can imagine for one layer, it aggregates a one hop. It's one hop neighbors. So when you stack two layers, basically the information flows from two hop neighbors to each node, and it becomes more like powerful. And in DGL, although the equations looks like a little bit complicated, a little bit like busy right now, but in DGL we have already provided the implementation of many popular neighbor aggregation modules we call graph convolution modules. They can all be invoked easily with one of codes, just like some other modules. And you can see, if you click this link, you can see all the like a graph, the different convolution modules we provided in DGL. And here, that's why in our example, for GraphSage, we can just import it from DGL.NN package. We import this SageConv, and we can build this GraphSage, the two-layer GraphSage model very easily. So here, for people who have experience with PyTorch, it is a very relatively simple code. You define a GraphSage module, inherit the end module. You define two submodules, conv1 and conv2. They are all like computed from, they are all initialized with this SageConv modules from DGL. You specify what are the input feature size and output feature size. And you also specify what is the aggregation function here. So the aggregation function is customizable in SageConv, and what we use here is the mean, basically averaging the neighbor representations. And then now we perform forward computation, and you can see there are two inputs. The first one is the graph structure, and the second one is the input feature, or the input node feature. And then we go through each convolution layer and applied the nonlinear function, and go through that convolution, another convolution layer again. So you might wonder, okay, you have the nonlinear function here. What happens to the W, right? The W is basically the training parameters, right? And where is that? And it is actually inside of this SageConv. So we'll see that later. So you don't need to worry about that. So you can think about each convolution has its own parameter. So when you're stacking that, you don't need to care about that. It is already initialized properly. And during backward propagation and gradient update, it will be updated accordingly as well. Okay, after you define this GraphSage model, now you can create this network object, right? You can specify what are the input feature size, hidden feature size, and output feature size. So here, because remember, our input feature is this embedding, right? The embedding has size 5. So that's why the input feature size is 5. And the hidden size is 16, and some arbitrary number you can tweak. And the output is 2, because we only predict two classes. One is the instructor, another is the president. So which basically there are only 2 communities in this network. So that's why the output is 2. And okay, we can run this, and we define this network. And now we set up the training loop. So the training loop is also quite typical. You can see we created the optimizer using Atom, and we put the parameters into it. Remember, we also need to like feed the node embedding parameters as well. And the training loop is is as follows. You have outer loop like training for several epochs. You do forward propagation using your defined network. You get you give it the graph and the node features. You get the logits, which is basically a prediction of each node, and you apply cross entropy loss. So this is basically cross entropy loss. And remember, it's a semi-supervised setting. So not all the labels are visible to the training loop. Only the labels, only the nodes that are labeled. So that's why here, when we compute the loss function, we only look at the logits of the label nodes and labels of the label nodes and compute the loss out of that. And then we do backward propagation and gradient update. And the DGL actually is compatible with PyTorch, PyTorch's autograd, so all the gradient will flow back successfully. So we can run this training code. You can see it trains quite quickly because the graph is pretty small. And we can also evaluate this task by looking at the accuracy. And you can see this accuracy is pretty high. Now we are using all the labels, and we look at the prediction of all the labels and predict, okay, and you see, okay, the accuracy is pretty good. Okay, so this completes the training and how you define a neural network and train it. And I want to show you something more interesting, like we can also visualize the results to see how this neural network works. And remember, when we use this graph neural, when we define this graph neural network, after we do forward propagation, the output for each node is a vector of length 2, right? Because you have 2 classes. So the output is of length 2. And because it's like two size vector, we can plot that onto the plane and to see how the neural network get a better and a better representation during the training, and why it classifies these these nodes very correctly. And so this visualization is like follows. You can actually run the code here, but it requires a decoder, FFmpeg decoder, which is not available in this particular notebook environment. So this is my laptop, so I have installed that, so I can run it, but you guys may find some error. So I also paste one of the result here. So you can see in epoch 0, all the nodes, like the blue nodes, the bluish node and the reddish nodes are actually the nodes belong to different communities. And you can see in the beginning, they are actually clumped together, and you cannot actually classify them very easily. But during the training, you can see the neural network tries to disentangle this community and separate them in a 2D plane. And this is why it can actually perform this community detection in a high accuracy. And only using 2 labels, labels of 2 nodes, the 0 node and the 32 nodes. And you can see this is animation. Yes, and you can see this is like the real animation, like generated on the fly. It's quite similar. In the beginning, it's very fuzzy, but now it becomes, after during the training, it becomes better and better. Okay, so there are some take-home exercises. You can actually play with the GM models we define here. We define here this graph sage model. You can try to replace this sage convolution with other convolution models in our list. And you can play with it or tweak with different hidden size or embedding size to see whether you can get a better result or train faster. So any questions for this session?
I think there is a question in the chat.
Oh, I see. How can I?
It's, so it's near share screen, like there is a button near participant, there is chat.
Oh, I see. Okay, it need to be sorted by. So the first question is about. I see. So the first question is about the data. So does it require to be sorted, right? Like whether it's. Let me take a look at this. Okay. So here you can see, like in our example, it is sorted, but it is not required. You can actually have arbitrary order of your the edges. And that's why, so in each edge, we actually assign an integer edge ID. It also starts from 0 to the number of edges. So here we have 156 edges. So it starts from 0 to 155. And if your order is like random, so now the first edge will not be 0, 1, maybe 33 to 30 is completely like legit in DGL. And but remember, when you set the edge features, which is a tensor, right? You need to make sure that, for example, the first row, the first element or the first row of that edge tensor corresponds to the edge feature of the first, the feature of the first edge. So that's the only requirement. Okay, so the second question is about the W matrices in SageConf. Yeah, so I also talk about this, like, okay, during the explanation. So in the last session, you will look at, okay, how this SageConf is implemented. So you will get more sense about, okay, where this W matrices are. So yeah, you will see that later. Okay. If no more questions, let's move on to the next one. So link prediction one. Okay. Okay. Let's click this link prediction notebook. So in this notebook, we'll show you guys that, okay, we can use the same. Oh, there's another question from the chat. Oh, there are more questions. Okay, so I run my notebook. However, the accuracy is like 80%. Yes, you are right. So the because this is actually a pretty hard task. We only have like two labeled nodes, so it's not very stable. So depending on your initialization, so that's why the initialization of your node embedding is so critical. Depends on initialization, you will actually have different end up results. So you might want to run the notebook for several times, and you will see that you can have like sometimes have a better like accuracy. And because of this semi-supervised setting, it's the variance is pretty large. And yeah. And let me see the other one. If you use a general model like GraphSage, can we define our own aggregate methods? Yeah, so we will look at how the GraphSage, the aggregation method is implemented. You can implement your own aggregated methods. We will see that later in another session, in another notebook. Another question, how may I access the notebooks, please? Okay, so maybe you come up, you come late. This is how you can take a screen of this, like send an email to this request mbin.mxl.io. You can get a service that can show you how to run it. You can also join our Slack channel to get a notebook. And all the notebooks are available in GitHub, so you can download that. We'll post that link in the chat later. Yes. Okay. So let's move on to the link prediction one. Okay. So here we want to show that we can use the same graph neural network we defined before to achieve a link prediction task instead of a node classification, a commit detection task. So basically, we will show you how to prepare the training and testing set for link prediction, how to build a GN-based link prediction model and train the model and verify the result. Okay, again, let's start with the first cell. We just run it, and everything works fine. And and the first thing we need to load the graph and the features, right? And this has been done before, so we just run the code, and you can see we have these embeddings and graph structures like here. Okay, so for link prediction tasks, a tricky thing is how to prepare the training and testing set. So remember, before we have a semi-supervised setting, each node, we classify a label for each node. So we can split, for example, the labeled nodes with some into training data set and testing data sets. But for link prediction, it's actually trickier. Because the goal of link prediction is to predict whether the edge exists or not. So that's why in the data set, you will have two kinds of edges. One is the positive edges, one is the negative edges. And the positive edges are those you want to predict they exist, while the negative edges are something you don't want the model to predict them in the graph. So for positive edges, it's not hard, because when we look at the graph itself, all the edges in the graph are something we want the model to predict they exist. So that's why here we randomly pick the 50 edges for testing and leave the rest for training. And you can do so by first get all the edges using this g.edges APIs from DGL graph. Now you get two arrays. U is for the source nodes and V is for destination nodes. And we just randomly pick we just randomly pick 50 edges from them. So what we did here is we generate EIDs from 0 to the number of edges. We permutate it randomly, and we extract 50 edges as the test set and the rest as the training set. So this is all straightforward. We just run it, and this is done. And for negative edges, it's a little bit tricky, because remember, if we consider all the possible edges in the graph, it has a complexity of O(n) squared, where n is the number of nodes. And because the graph is usually very sparse, so this space is huge. That means the number of negative edges compared with the number of positive edges is much larger. And in reality, in real cases, we will perform negative sampling. Like, okay, choose some of the edges, negative edges, as the training samples and verify it on the others. And there are a lot of different papers and work about how you choose these negative edges smartly, but this is out of scope of this tutorial. And in this example, our graph is pretty small. We only have 34 nodes. So what we can do here is we can actually enumerate all the missing edges and randomly pick 50 for testing and 150 for training. So this is how we do it. We first, using the U and V, basically the source and the destination arrays, we create a side-by-sparse matrix, adjacency matrix, and we negate that adjacent matrix. So now the one in that adjacent matrix marks the negative edges, and then we use numpy or where operator to get all the coordinates. And afterwards, we can just using numpy choice to choose 50 edges for testing and 150 edges for training. So this is feasible for very small graph like what we have here. But again, for larger graph, negative sampling is desired. So we can run this code and we get all these negative edges. And finally, we can put all the positive and negative edges together to form the training and testing split. So here you can see we can concatenate the positive edges with the negative edges. And we also assign the labels correspondingly. For positive edges, the labels are 0, the negative edges label are 1. So it's a binary classification task. So we can run this. And now the test and the training data set has been completed. Okay. now we define the models. And the goal here is to show you that, okay, this graph stage model we defined before can be used in this task. So you can see basically the model is the same, right? You can see you have two layers and a nonlinear action activation, and you just run the codes and your model is defined. And to optimize this model, we need to apply a different loss function because of a link prediction task. So here, what we used is when we compute the logits of each vertices, we need to compute a score for each pair of nodes. And we need to prepare a score of it. The score need to be between 0 and 1. 0 means the edge is a positive one, that it exists. 1 means that it is a negative one. So to achieve that, we basically use a dot product. So you can see the mass equation here. Given any pair U and V, we compute HU transpose times HV, and we apply a sigmoid function on it to cast the value into 0 and 1. And once we get this prediction, we apply this loss. We try to optimize the model with this loss function. So this loss function is essentially a binary cross entropy. So here, let's look at how it is implemented in the training loop. You again create an optimizer, and in each epoch, you first compute the logits of each nodes, and this is how you compute the dot product score. Here for each logits, because you have this training U and a training V endpoints array, you do a tensor lookup. You get the corresponding logits, and you perform unwise multiply, and do a reduction on the second dimension. Now you get the dot product. Apply a sigmoid, you get a prediction that is between 0 and 1, and you apply a binary cross entropy loss on it. And then the backward is the same as before. And then we can run this. You can see it also trains very quickly. And we can verify the result on the tested set. And yes, and you can see the accuracy is around like 80%. Okay, so this is like a very simple example, but also a quite complete one. It basically tells you, okay, how given a graph, and how can we prepare the training and testing data sets for link prediction tasks, how we reuse the graph neural network module to produce a better representation of each node that can be useful to compute a good a good prediction of each edges for a link prediction task. Okay, so is there any question about this one? Okay, there's some questions about in the chat about can it support TensorFlow version? Yes, we have TensorFlow support in the latest release. So the answer is yes. Okay, since we have like around half an hour left, so we can go to the advanced notebook called another advanced topic called message passing. So we will look at, and I think since many people have been asking about this, we will look at how the SageConf module is implemented in DGL. And so basically we dive into the SageConf module, and we will see how we use DGL's message passing APIs to implement these kind of modules. And you will see how we can design a new convolution module using this message passing APIs. Okay, let's start with import some packages. Okay, so as you can see here, this is the SageConf equations, right? I think you have already familiar with that. Here is its implementation in DGL, and you can try to compare with the mass equation with the implementation. So here, the SageConf has one submodule called linear module. This is where the W, the trainable parameters, is. We basically use PyTorch. So this NN is PyTorch torch NN. We basically use PyTorch's linear layer to implement this like a W times the concatenation operation. And the input size is input feature times 2. The output size is the output feature size is given back to the SageConf. The reason why this one is input feature size times 2 is because you have this concatenation here. You have basically two vectors, right? Like one is your self representation, the self representation, and this other is the neighbor representation. So that's why it's times 2. So, and the forward function, you can see how it is implemented. So again, the input is, the first argument is the graph itself, the graph topology. And the second one is the input node feature. And here we start with this g.local scope. So this local scope is you can think about it's like a guardian syntax, because remember our graph has these n data and the e data dictionaries, right? And when we set this features, node features or add features into graph, sometimes we forget to pop them out and leave it there, so it is not very friendly for like garbage collection. So that's why we have this helper function called g.local scope. So within this scope, all the features, all the like node data or edge data set to graph G will be automatically popped out after we exist this local scope. So for example, the edge here. And when we implemented this aggregation function, we actually use this g.update all syntax we saw before in the slide, in the PPT, in the presentation before. It has actually two parts. The first one is a copy U function, and the second one is a mean aggregator, the mean aggregation function. So essentially, the g.update all function tells you three things. The first thing is, the first argument is called the message function. The message function here is imported from DGL's function, DGL.function package. It basically tells the system, tells DGL that, okay, I want to copy the node feature h under name h from the source node, because it's U, and we have this convention like U is for the source node and V is for the destination nodes. We copy the feature of the feature called the name called the h, and use it as a message. The message name is M. And then later, the message name M is matched by the reduce function here. The reduce function fn.min m hna means that, okay, I wanted to aggregate the received messages under name M and produce a new node feature called hna. So basically, this is, this is how this message function and the reduce function looks like. And update all tells DGL that, okay, we want to trigger this send and receive, and the copy, the message function and the reduce function on all the nodes and edges. So you can see this one line of code actually tells three pieces of information to the system. And this actually completes the equation, the first equation where you can see basically the copies, right? The copy U, right? The copy U basically gathers the HU K minus 1 from this neighbor node, and this aggregate here is the mean aggregation. You can actually use a different aggregation. We'll talk about that later. But here we use a mean aggregation to aggregate all these neighbor representations. And after we after this update all call, the HNA is generated in g.n data, so we can get it. We can get it from g.n data. And to finish the second equation, we concatenate them together along the second dimension. We apply a nonlinear function, and then we'll apply the affine transformation using Torch's linear module and apply a nonlinear function. So this finish the whole SageConf module implementation. So it's a simplified version, but it actually gives you a general idea of how it is done in DGL using these message passing APIs. Okay, so let's talk about this message passing APIs. These are the central pieces in this code. So in DGL, this message passing APIs are actually inspired by the message passing neural network proposed by Gilmer. Essentially, the following framework, you can see these three equations. They found that these three equations can summarize a lot of different graph neural networks proposed before. And you can see the first one, it basically called the message phase. You have this capital M, which is the message function. It has three inputs, HV, which is the destination node, HU is the source node representation, and also the edge representation. It takes all these three information and get a message on this edge. And after that, you apply a reduce operation, a reduce phase, where you aggregate all these messages together to get aggregated version. And this sigma here can be customized by different things, like not only sum, but also like max, min, or something, max, min, something like that. And later, once we get the aggregated messages, we apply a reduce function by a reduce function, an update function by this capital U. It accepts two information. One is the node embeddings of its own, and the other is the aggregated messages, and it produced the higher layer representations. So you can see this is basically how we implement it. Actually corresponds to the update all function very nicely, right? The first copy U message function corresponding to the first equation, and the second argument, the reduce corresponding to the second one, and the update all will trigger everything for every nodes, and the update function is actually implemented directly in the forward function. Okay, so now you're asking, okay, we have many. We want to have many different like message function, reduce functions, right? And for example, we want to have a different aggregator, like not only min, but how can we do that? In DGL, under this DGL the function package, we actually provide many different combinations, basically. So for example, here you have copy U. We saw that before, and you also have like copy E, where we can copy the edge data instead of the source data, and to form a message. And we also have some more complicated combination, like you can have a binary operation between the source and destination, or between the source and source node and the edge data, source data and the edge data. So you can see there are some U, for example, U multiply E, which means, okay, in the message phase, this N, I wanted to multiply this HU with EUV to get, for example, a weighted message. And you can see all these messages and is their API document here. And for the reduce function, we currently provide these 5 reduce function, so it can help you to implement different modules. So let's take a look at an example. So here is an example where we modify the SageConv a little bit. We implement a new SageConv that also takes also have an edge weight, also takes an edge weight as an input. So you can see here the submodules are still the same. And in the forward function, you have an extra argument. The extra argument is a tensor, the weight tensor. And to apply that weight tensor in the message passing, here we basically set this weight tensor into g.e data under some arbitrary name called w. And the message function now is different. It uses u multiply e. It now has 3 arguments. The first one is the source node feature name. It is still h. The second one is the edge data name. It is now w. And the result is the message name, which is matched by the reduce function here and produce the hna like feature. And you can do that the other part is the same as the original one. You can see the other part is the same as the original one. Yeah. And this is how basically how you customize an NN module in DGL, or write your own NN module using this message passing API. And also, people may wonder that, okay, you already, although you provide all these built-in messenger reduce functions, they are not like everyone. They are not everything, right? You can come up with some function that is not covered in this list. So how can we do that, right? So actually in DGL, we allow even more customization by user-defined function. So basically, the update all, the argument, the second argument, the first argument, the second argument, they can accept a user-defined function defined in pure Python. So here is an example. So this u multiply e UDF is a native Python function. And it is this implementation is actually equivalent to our u multiply e built-in function. So you can see this is how it is done. So basically the argument to this UDF is in edges. So it is type like we call it edge batch. Usually you can it has three attributes: source, test, and data. And you can get, for example, source dictionary and data dictionary. And for edge, for u multiply e edge w and m, it basically means that, okay, I get the edge features out of the source data dictionary, and also the w feature from edge itself, multiply it, and return the message under name m. And you can also, for example, if you wanted to do a copy u UDF, it's essentially something like this. You can just return the source node data and as the messages. And you can, as you can imagine, that you can customize this UDF with arbitrary code, so it can express a lot of different message passing neural networks. Okay, some recap. So we go through the implementation of the DGL, the SageConv module. So you can see this SageConv module, and we go through how it is implemented with DGL.update or a message passing APIs, and what are the message function and reduce function. And we show that we have a lot of built-in functions to customize new modules. And you can also use user-defined function if they cannot cover your case. As a rule of thumb, in DGL, we recommend people to first look at our modules. And if you are working on something like, okay, you want to define your own module, then try to think about how can you implement it in using DGL's built-in function, like you copy U or you multiply E, this kind of stuff. Because underlying in the system side, we didn't cover that. We won't cover that in this tutorial. In the underlying system, we will, because we know what you are doing for this message and the reduce phase, we can optimize it very aggressively by mapping it to some very efficient GPU kernels. So it's much, much more efficient than you provide us like a native Python function like a UDF here. The UDF is suitable if your graph is small, for example, or you wanted to do a quick prototyping. In such case, it can easily implement almost everything. But in terms of, for more efficiency, we highly recommend you guys check out our built-in functions, and we found that it can cover most of the cases. I think that's it for my sessions. Any questions? Yeah, I finished earlier, way earlier, but yeah, if you have any questions, I'm happy to answer.
Okay, I can do a question. This is Puya. Can you, maybe we will have a session on the big graphs, but can you give us an idea of the memory size, like, and then like some estimate, some rough idea of, like, I don't know, 100 million nodes, what is going to happen, how much is going to be the memory size, is it efficient? Because I know that you're working on the distributed version, but as it is now, this framework, like, what are the biggest computation you have done with it, and if you can give us like some estimation of the GPU usage and memory usage, would be great.
Oh yeah, that's a question for Da. I think, Da, are you here? I think you have tested a very large graph, basically the full freebase graph, right? So how many nodes are there, and how large is?
Sure. I can take this question. So actually, for DGL, we actually did multiple experiments on running a large graph. So I mean, like 1 year ago, we already tried running a graph with like, I remember, and we tried a graph with 500 million nodes. And the memory consumption for that graph is, the graph structure probably takes like a couple hundred gigabyte, and then the node feature, the node feature really depend on how many, what is your feature dimension, right? And also, so mainly your feature dimension. So suppose your feature dimension is 100, and then you have like a 500 million nodes, and that probably adds up to, let's say, a couple hundred gigabyte. So to train a graph neural network at that scale, we probably need, to be safe, we probably need like a machine or a cluster of machines with about 1 terabyte of RAM. But then you mentioned the GPU training, because in the GPU training case, we never really store the graph structure or the entire, all the node features in GPU. We still store all those things in CPU memory. So we only construct the mini batch and then move all the move the data required for the mini batch to CPU to GPU for computation. So we don't really, in that case, we don't really consume much GPU memory. Does this address your question?
Yeah, it was great. Thank you. If nobody is asking, I'm going to ask another one, the same.
Yeah, go ahead.
Yeah, so like, so I get the point of the very, very large 500 million, let's say, node, but what are the typical node size that you have been working on with, I don't know, like 40, 50 gig of RAM, something's a little bit, let's say, more. So what are the typical problems that you have solved and that you have seen, like in terms of like industrial application, no? So like some nodes, some graph with manageable with like 40, 50, maximum 100 gig of RAM.
Oh, for a machine with only 40 or 50 gigabyte of RAM, what is the solvable problem?
Yes.
Graph size? Is that your question?
Yes, yes. In your experience, obviously, yes.
I guess it still depends on your feature dimension, right? I mean, some people, it varies a lot. Some people has, as far as I know, some people has features like 10 to 20 gig, features for each node. Some people might have like hundreds. And previously, we always assume you have a very large number of features on your node. But that turns out it's not always true. So being said that, so let's say, I mean, really the memory consumption is your graph structure and the node features, the original node features. Because we are doing a mini batch training, the memory consumption from mini batch is almost nothing. So it's really the memory consumption from the graph structure and the node feature. Now, these two things are very easy to estimate. So for graph structure, we use CSR. So that means most of the memory consumption comes from the number of edges. And right now, what DGL needs to use about 16 bytes for each edge to store the graph structure, roughly. So then you can calculate if you have like a 40 gigabyte of RAM, how many edges you can store. And also for node features, let's say you have 40 gigabyte RAM, and each node you have required to 1 kilobyte of RAM to store the features. Then you can also calculate how many nodes you can support, and then you can add them together. So
I think I get the. So there is no. So you haven't applied any compression on in terms of like keeping in memory, let's say a large number of ages. So is there any compression involved?
Okay, so at this point, no, but it is in our plan. And we realize that graph structure in a lot of cases actually consume a lot of memory. So we start to really think about what is the best way to compress the graph structure. I mean, ideally, I would say if we do it well, we probably can compress the memory by like using like about 2 to 3 bytes for on average for an edge. So that will really allow you to store much larger graph with many more edges. But I mean, it's very difficult to compress the node features, right? Unless you want to use some low precision floating point.
Yes, yes. Thank you very much. Yeah.
So allow me to add something to that answer. So for this kind of large graph, we usually recommend mini batch training, and so mini batch training would be introduced by Dai in the next tutorial. And you may notice that technically you don't have to store like the entire node feature set into the memory. So essentially you can like sample any mini batch and then read the corresponding node features from a file. But the efficiency would be kind of slow because you need to like constantly reading stuff from the disk. And we didn't really like do experiments for this kind of scenario, but yeah.
Thank you very much. Yeah, it's great.
No problem.
All right, if there's no more questions, I think this ends the morning session. The afternoon session will start. I think it will be like 1.5 hour break for lunch, and the afternoon session will start at 2 p.m. I guess. Yeah, let me check out the schedule. Yeah, 2 p.m. So the afternoon session will be more advanced topics about GN training on large graphs and GNs for real world application. So see you guys.
Hello, everyone. It's yeah, so I suppose now it's 2 p.m. in the Beijing time. Maybe you can start the afternoon session. So so in the morning, we talked about graph neural network in general and how we can use, we also introduced deep graph library and how we can use deep graph library to perform graph neural network computation for downstream tasks such as node classification and link prediction. And in the morning session, we in the hands-on this morning's hands-on session, we are using a very small example to illustrate the programming interface and how we can formulate the node classification, the downstream tasks using graph neural network. And in the afternoon session, we are going to address more real-world application and the problems. So we are going to talk about how we are going to train a graph neural network on a giant graph in DGL. And basically, this will be covered by this session. And we are also going to talk about how we apply a graph neural network in DGL to real-world applications such as recommendation. Okay, so and also this morning, George briefly mentioned how we potentially can perform mini-batch training on graph neural network. So this session, I will first start with slides to talk about some of the intuition of why we want to formulate the graph neural network mini-batch training like this. And then we are going to I'm going to show you some code to see how actually DGI, what we provide in DGL to help you to perform mini-batch training. As you already, I suppose some of you are from the industry, then it's very common that you encounter some large graphs. So example is a social network. We can easily get a social network with millions of nodes or even billions of nodes. And in the case of knowledge graph, we can also easily to get like millions of entities and even billions of millions of entities and or even billions of relations. And in the recommendation setting in the industry, we can also easily to get millions of nodes. So now if we perform a full graph training on a graph of this size, by full graph training, what I mean is we run the forward computation and the backward computation on the entire graph. Then the memory consumption of a graph neural network model will be in proportional to the number of nodes and the number of edges. And if a graph has like billions of edges, then the computation will require terabytes of data or terabytes of RAM and memory. So it's very actually, I mean, nowadays, it's even nowadays still not very easy to get a machine with terabytes of RAM. So it's very easy that if you perform full graph training, you will run out of memory. But if we look at the mini batch, how we train a deep learning model, we see that we usually use mini batch training for deep learning models. And here is a very short review of how mini batch training was done in deep learning domain. So we have a data set, and this data set has many data points. And what we do for mini batch training is we randomly sample, usually we do uniformly randomly sample data points from the full data set. Then this will construct a mini batch. And then we perform the deep learning model on the mini batch, which will allow me to estimate the gradient of the model, and we use the gradient to update the deep learning model parameters. The reason we can uniformly sample data points from the entire data set is because all the data points are, we made the assumption that the data points are independently and identically distributed. However, this is not really the case for graphs. So if we assume data points are the nodes in the graph, and then the edge actually represents the dependencies between the data points. So that means on a graph, nodes are not independent. So we cannot really sample nodes uniformly randomly. Now, now the question is, if we want to sample nodes, how are we going to deal with the dependencies? To answer this question, let's go back to and have a look at what a graph neural network usually do. So here I use a GraphSage as an example, simply because GraphSage is a very popular graph neural network model, and it's also a very simple model. And the other reason is we found that GraphSage is a very good example to illustrate a very typical problem that happens when we perform mini batch training on a graph neural network. So in the morning, I think Minjie already described what a graph neural network does. So in here, I will just have a very short recap what this graph neural network is, GraphSage is formulated. So basically, what we if we want to compute the embedding of node V for layer K, we need to get those this vertex V's neighbors embedding from the previous layer, and then we perform the aggregation over the neighbors embeddings, which generates this aggregation result. And then we need to concatenate this vertex V's embedding of the previous layer with the aggregation result, and then perform a linear projection and a nonlinear transformation. So if we look at a multi-layer, or we say, let's say, if we look at the two-layer graph neural network from the perspective of a vertex. So if you want to compute, for example, if you want to compute in this example, if you want to compute the embeddings of node 1 of layer 2, what we need to do? So we need to gather all node 1's neighbors, the neighbors embeddings of layer 1. However, the problem is, so basically we need to get the embeddings of node 2, 3, 4, 5, 6 of layer 1. But the problem is we actually don't have the embeddings of those nodes of layer 1, right? So we need to invoke the computation recursively before we can compute the embedding of node 1 of layer 2, we need to compute the embeddings of the neighbors. We need to compute the embeddings of its neighbors of layer 1 first. So we need to perform this graph sage computation on node 2 for layer 1. And in this case, node 2 has a neighbor, only one neighbor. It's actually node 1. And then to compute the embedding of node 2, what we need is we need node 1's embedding of layer 0. When actually the layer 0 means this actually is what we need is this node 1's input features. And then we need to concatenate node 2's embeddings of layer 0 as well, which basically we need to concatenate node 2's input features with the aggregation result, and that allow us to compute the embeddings of node 2 of layer 1. Similarly, we need to do it for node 3, node 4, node 5, and node 6. Now we compute all the embeddings of its neighbors, the embeddings of its neighbors of layer 1. We can go back and compute the embeddings of node 1 of layer 2. So what this means, if let's take another view of this computation. So basically, we will see actually a computation or data dependency. So in order to compute the embedding of node 1 for the second layer, we need to get all its embedding, its neighbors embeddings, as well as its neighbors and neighbors embedding. So here, actually, I want to show you a very, very small example. The graph is really small. We already see that dependency is huge, right? So if we apply this method on actually the real large graph, and this neighborhood size will actually increase exponentially with the number of layers. So and if we apply this, another problem is in a lot of real world problems has a power law distribution, which means some of nodes has like thousands or even or in the extreme case, they might have even millions of nodes. Then it's the computation dependency, the dependency will be huge. The computation and the data dependency will be huge. It's not really practical to perform mini batch training in this way to actually to train a model. So typically, when we perform a mini batch training or we want to generate a mini batch on a graph, we usually have we usually need to perform two steps. The first step is to randomly sample target nodes. And the way we sample the target nodes is we can sample the target nodes uniformly at random. And once we have the target nodes, we can start to sample their neighbors randomly. And this the second step is actually equivalent to pruning the computation and data dependency. Basically, we want to reduce the dependency in this computation graph. Actually, there are many different ways, different strategies for us to sample neighbors. There is a very simple way, such as like a neighborhood sampling, and there are more advanced, more complex way to sample neighbors. And for example, we can use like control variant based methods to sample neighborhood and perform aggregation. And we can also use layer-wise sampling or even random walk sampling. There are many different methods that have been developed in the past few years. And actually, DGL implemented quite a few of the different strategies. And if you are interested, you can go to the DGL repo to take a look at those different methods. But in this tutorial, we are just going to focus on the most simple one, basically the neighborhood sampling. So what the neighborhood sampling does is this. So it will just sample the neighbors from the neighbor list of a vertex. So basically, we want to reduce the number of neighbors, and then we do it recursively. So, for example, in this case, for this node 1, we will only sample 2 neighbors, 2 and 4, and then we do it recursively for node 2 because node 2 has only 1 neighbor, so we will just keep this neighbor. And for node 4, it has many neighbors. Then we will sample 2 neighbors, 7 and 8. And usually we sample those neighbors uniformly at random. But of course, we can apply the more advanced strategies to sample neighbors. And after we sample the neighbors, we need to adjust our neighborhood aggregation accordingly. And because, I mean, previously, if we look at the neighborhood aggregation, what we do, I mean, the neighborhood aggregation for different graph neural networks, such as like GCN or GraphSage or many other models, usually what we do is we sum over its neighbors embeddings over the previous layer. But this will give us the accurate the embedding for this neighborhood. But if we do neighbor sampling, we can no longer compute this NV superscript k accurately because we cannot see all its neighbors, right? So what we can do is we can only estimate this aggregation result based on what we have seen. We can see from the data. So this n tilde v represent this sampled neighborhood. So we have to we need to, after we sum over all the sampled neighbors, we need to rescale the embedding according to the original neighborhood size and the sample neighborhood size. That allow us to estimate the aggregation result. Of course, this is not a very accurate. This is not going to be a very accurate estimation, but this is the best we can do. So usually in practice, if we do perform neighbor sampling like that, and if we the sample neighbors is reasonable, is a reasonable size, we can train our model pretty accurately. So usually it works out. So okay, here in summary, what we do with mini batch training in graph neural network is we start from this full graph, we sample some target nodes, and then we sample its neighbors, multi-hop neighbors to construct a mini batch. And then we feed this sampled subgraph, sampled this mini batch to a graph neural network to estimate its model parameters and to update its model parameters. This is how we can do in theory. Now let's have a quick look at how we can how we can use DGL to construct a mini batch in practice. And before we actually really jump to the notebook to see the code, because I didn't want to make sure that some concept is clear for everyone before we actually look at the code. So in DGL, when we construct a mini batch, usually there are 3 steps. The first step is to as we have as I said before, the first step is to sample the target node, and then the second step is to sample multi-hop neighbors of the target nodes, and then the third step is to construct a mini batch, and we construct this mini batch data structure in such a way that we can reduce the memory consumption by a lot. So the first step is to sample target node. Actually, this is done outside of DGL. And DGL doesn't really provide any functions so far to help user to sample target node. But this is actually very, very simple. If you want to sample target nodes uniformly, one option is you can use a NumPy random choice to sample the target nodes, or the other, we can use like a PyTorch data loader to sample target nodes, or you can use any methods you like to sample the target nodes as you wish. Then the second, then we need to sample neighbors of the target nodes, and the DGL provide one function called sample neighbors that allow us to sample neighbors of the target nodes for one layer. So the way we do that is when we call sample neighbors, we need to pass the entire graph G. The entire graph G and a list of seed nodes, basically the target nodes. And then we user need to specify the number of fan out, which means the number of neighbors we want to sample for each node. Here is this one visualization of how it works. So suppose we have this full graph G. We pass the G to the sample neighbors. And then if we want to sample the neighbors of the target node 1, then we pass node 1 as a list. And then we specify, well, you want to sample 2 neighbors, then it will be, the fan out will be 2 here. And then this neighbor sample neighbors will generate a subgraph, all this graph G. So the subgraph will contain the same number of nodes, but it will only contain a very small number of edges for the incoming edges of the target nodes. So because we specify there's only one target node and there are only 2 edges, we want only sample 2 edges, 2 neighbors for the target node, then we will get only 2 edges in this subgraph. So that means all the rest of the nodes will actually become empty nodes. Similarly, we can do similar neighbor sampling for another layer. And then in this case, we will provide 2 and 4 as the seed node. And then again, we specify we are going to sample 2 neighbors. So for node 2, because it has only, node 2 has only 1 neighbor, so it will get 1 neighbor here. And then 4 will have multiple neighbors, and it will get 2 neighbors randomly. So here in this example, we get like a node 7 and node 8. And the remaining nodes will become empty nodes. Okay, so the third step is actually to construct a mini batch, a data structure. And what DGL provide is a function called, one thing I want to mention is that after we generate this block, this 2 subgraph, we can actually already perform message passing on the subgraph to perform computation. But except the only problem is this 2 subgraph has many nodes. So if we perform message passing on it, we will it will consume a lot of memory. So that's why we designed another function to construct a new data structure that is much more memory efficient. So what this 2 block does, it does a few things. The first thing is actually it tries to compress the sampled subgraph. So remember that this sampled subgraph has many empty nodes if this is if it is sampled from a giant graph. So it will remove all the empty nodes, And then another thing it does is to construct, to take this input, this subgraph, and then to construct a bipartite graph for message passing. So in this example, we will put all the destination, when we construct this bipartite graph, we will put the destination node on one side and all the source node on the other side. And in this example, the source node, in this example, there are 2 source nodes and 1 destination node. After we're doing that, we actually will relabel all the nodes. So in this case, this 1 destination node will get a local node ID 0, and then this 2 source node will get the local node ID 0 and 1. So in this way, this subgraph will, this bipartite graph will only contain 3 nodes and then use a very, very small amount of memory. Similarly, we do we need to call the 2 block on another sampled subgraph to construct this bipartite, more memory compact bipartite graph. Okay, so far we have seen how all the APIs DGL provide to help you to sample mini batch. But there is still one problem that actually this is a very common problem exists in mini batch training. And that is, here I will just use this graph stage to show you what the problem is. So remember, when we if we want to perform the graph stage computation, we need to get all its neighbors embeddings of the previous layer, as well as the embedding of the target node from the previous layer. But the problem is this target node does not really exist in this sampled subgraph, right? So how are we going to get the embedding of the target node from the previous layer? So there is one trick we played. We actually built into this 2-block function. That is, this two-block function actually has an argument called include destination, so include the DST in CSR. So what it means is when we turn on this flag, it will put the destination node in the source node as well, even though there's no edge between these 2 nodes. And then when we relabel of the destination node and the source node, this node 1 will get 0. And then other source node will get 1 and 2. So why are we doing, so how does this help? So here is one illustration why this strategy actually helps us to perform mini batch training on graph stage. So let's say we want to compute the embedding of node 1 for the second layer. Sorry, this is second layer. We need to get the embedding of node 1 from the first layer. So the trick after we play the trick, so node 1 basically is also here, and in this way we will when we perform the computation, when we construct this the block or this bipartite graph for the first layer, we already we get its neighbors, right? So we can so that we can compute estimate its embeddings of layer 1 in the same way as other nodes. So I mean, this trick, I mean, you can do this trick yourself, but we found that if we do it for you, it might be may simplify your coding effort. So that's all for my slides presentation. Does anyone have any questions about all of this the mini batch construction procedure, as well as what on the questions about what the sampling API DGL provides?
So I can ask you a question. So this is one way to do mini batch, no? So have you done like is that yeah? Do you is it already implemented some other way to do mini batch, or this is the only way?
So I'm very curious. What is the other way you are thinking of? So we actually explored multiple. We actually explored another way before. Maybe it's a similar way, but we found this way allow us to implement models such as graph sage or graph attention very easily. And
yeah, so I don't have one specific now. I would need to think about it, but yeah, I was just curious if you have done some other tests. Okay, so and the main reason would be like effectiveness in this case, like not really efficiency. Like
oh yes,
yeah.
yes. So yeah, so right now we actually did a lot of tests internally, and we previously we have one implementation. We implement everything in C, and then we tried this strategy, and then kind of like combining the C code with Python code, and then we realized when we use multiprocessing, even with this with some Python code in the process in the implementation, it is still very efficient. Most of the computation overhead actually happens inside the C code, and that we can already optimize. And we also compare the pure C implementation and the Python mixed Python and C implementation, and the throughput we get is more or less the same.
Thank you.
Okay, so if there are no more questions, let's jump to the tutorial, the notebook, and to see some code to see what actually really happens when we call all those functions on a graph. So this tutorial, this notebook will again use GraphSage as for demonstration. And we have mentioned the formulation multiple times, so I will just skip that. And before we can run any computation, we need to load the DGL and all its other functions and modules. And because, I mean, in the morning, we also mentioned that DGL supports multiple backend. So it supports multiple deep learning frameworks. So in this tutorial, we are going to use PyTorch. So there's one question about, so are you using another app? Sorry, I don't quite understand this question. Oh, I see. Okay, sorry. Let me, yes, I switched to Chrome. I thought it will also have the, its screen is shared. Let me share the screen again. Can you guys see my screen now?
Yes.
Okay, good. Thanks for reminding me. So as I said, this tutorial, actually this tutorial is actually in this large graph. If you go to our notebook, you should see our this tutorial in this large graphs folder. Okay, so before we run anything, let's load the DGL and the PyTorch. And this tutorial will have two parts. The first part, we are going to show you how mini batch is constructed from a graph, and then how this mini batch will look like after we construct them. And then the second part will show you how we can perform mini batch training on this constructed mini batch training on of a graph sage on the constructed mini batch. Okay, so for the first part, to make all the visualization simpler, we will just use a very small toy graph. So we just manually create this toy graph with a network X, and then after we create it, we construct a DGL graph. So this toy graph will only have 12 nodes and 20 edges. So it's very simple. And this is a bypass. This is an undirected graph. To see, okay, so let's start something very simple. So if you want to sample mini batch for one layer GC graph sage, let's say, how does this this sample neighbor works? So again, as I showed you before, when we call sample neighbors, we need to provide the full graph, and then we need to provide the target node. So in this example, we want to sample, we want to perform the graph sage computation on node 4 and 6. So node 4 and 6 will be our target nodes, and then we want to sample two neighbors. So let's see. Oh, sorry, I didn't construct this graph. So after we call these sample neighbors, we actually we get a subgraph which has 12 nodes and 4 edges. So as I said, as I told you before, that when we call sample neighbors, it doesn't really remove the nodes. It only extracts some of the edges in the original graph. So, and you will still have all the nodes in the sampled subgraph. And then if we look at all the edges, then we see that we sampled two neighbors from for node 1 and node 4. Sorry, there are two columns. The first column is the source node, and the second column is the destination node. So we sampled two neighbors for node 4 and sampled two neighbors for node 6. So that's why we have four edges here. So after we after we get this sampled subgraph, we need to call this two-block function to construct a bipartite graph. A bipartite structure block, we call it a block, to help us to do more efficient message passing. So so here is what we can. Here we call this two block on this sampled subgraph, and which returns a block. let's so here let's see what we can we get from this block structure. So as I said before, this block is it's actually a bipartite graph. So if we print out the source nodes and the destination nodes, we can see that the destination nodes there are 2 destination nodes, and which are 4 and 6. And there are 5 source nodes. And 2 of them are actually the destination node, right? They are the same as the destination node. And the remaining 3 are the neighbors of the destination node we can see from here, right? So there are 0 to 7, and this is 0 to 7. So it looks like, so this is exactly what we were expecting. And then when we print out all the edges, when we want to print out all the edges, want to print out all the edges in the block, we see that all the nodes actually in this block is mapped to and is actually relabeled, and it's relabeled starting from 0. And so that means there's this, and then if we remap all those node IDs in this edges to the original graph, to the original node ID, then we get this 4, 7, 4, 2, 6, 0, 6, 2 again. So this is the same as here. Now, now let's take a look at what we can get from if we want to do multi-layer graph sage. How do we do that? So here we define a class called the neighbor sampler. It takes G as the input. G is the full graph, and then it also we user need to specify. We allow user to define the fan outs for each layer. So if there are 2 layers, then this fan out should be a list of 2 elements. Each of the elements define the fan out for each layer. And then when user calls a sample, this sample function, the user needs to provide the seed nodes. And remember when we construct this when we sample subgraphs or sample to construct those block data structure, we actually started from the target node. So basically, when I say target node, I actually mean the seed node. So we will start from the seed node, and then we construct the blocks in a reverse order. So basically, if we construct 2 blocks, then we'll start from we construct the first. So first we construct the second block, then we construct the first block. So that's why when we iterate over all the fan outs in the list, we do it in the reverse order. So and when we have the seed node and we know the number of this fan out factor, we can call sample neighbors to construct to get all the edges to get this subgraph for this block. So in this case, we need to provide this input graph, the seeds, and the fan out. Here in this implementation, I also use another function called in subgraph. These 2 methods actually are kind of similar. The only difference is this in subgraph will return a subgraph that contains all the edges of the seed nodes, instead of this one return randomly sample some incoming edges of the seed nodes. So the reason I need to implement this is because this is used for inference. when we perform mini batch inference. So we will see later why we need that. So after we get this sampled subgraph, we pass it to a block. We pass it to block, which generates this sampled block. And then then we need to proceed to the next block, right? So we need to get the seed node for the next block. And the seed nodes are the source nodes of the current block. Then after, then we need to put this constructed block into our block list. Because we construct the blocks in the reverse order, so whenever we construct a block, we should always put it in at the beginning of the list, so that afterwards when we perform message passing in a mini batch, we will actually perform the computation in the right order. After that, we return all the blocks, the list of blocks. Okay, let's execute this. And then here is the one example of showing you how we construct a mini batch of 2 blocks. Sorry, a mini batch with of 2 blocks. So when we create this neighbor sampler, we pass the full graph, and then we specify the fan out for each layer. So if we want to construct 2 blocks, we will pass two elements in the list. And then when we call sample function, then we need to pass the seed node. And in our case, the seed node actually is 4 and 6. So this will return 2 blocks, as we see here. And then this is the first block, and this is the second block. So let's see what we have. So in the second block, the destination node will be the seed node we just give to the neighbor sampler, which is the 4 and 6. And then the source node is exactly what we have seen in the previous simple layer example. And all the edges are more or less the same. For the first layer, for the first block, the destination node will be the same as the source node, will be the same as the source node of the second block. So it's 46720, and they are also they are stored in the same order. And then the source node will again also contains the destination node, and as well as some other neighbors. And of course, the first layer will be so the block for the first layer will be much larger than the block for the second layer. Okay, so now we have seen how we can construct a mini batch. Let's actually perform a mini batch training of a 2-layer graph sage and see how well it works. Maybe for this part, I'm going to reverse the order a little bit. So I'm going to show you how this entire the entire training loop look like before we jump into the model implementation. So to perform the training loop, we need to load the data. So in this in this tutorial in the notebook, actually I provided 2 data sets just for the illustration purpose. So the first data set is very, very small. It is a citation graph called PubMed. And this data set previously was commonly used by a lot of research papers. Now, in this citation graph, all nodes are papers and edges are citations. And this is DGL actually provides this PubMed dataset as one of the built-in datasets. And if you are interested, you can go to this link to see a lot of other built-in datasets provided by DGL. So the way to use this built-in dataset is this. So we call DGL data citation graph loaded PubMed, which this will return a dataset. And one of the fields of this dataset is graph. It stores the graph structure. So when we pass this graph structure to DGL graph, it will construct the DGL graph automatically. And then we need to construct the features and the labels of this dataset. So those features and labels are also provided by the dataset. And then we need to store those features and labels in the node as one of the node data in DGL in this graph. And also this dataset has already have the split for the training set, the validation set, and test set, and we are going to just use that. And so here we can see that this dataset is really small. It has like 20,000 nodes and 88,000 edges. Later on, I'm going to show you. I think we have enough time, so I'm going to show you how we can perform the mini batch training on a much larger graph. So now we have to construct this DGL graph, and then we need to construct this neighbor sampler. And again, when we construct the neighbor sampler, we need to provide the fanouts for each layer. So I put 10 and 25 here. The reason I do that is actually those are the fanouts used by the original Graph Sage paper. So I just want to follow their suggestions. Another thing is actually, so in my slides, I said we needed to construct a mini batch. We have 3 steps. The first step is actually to sample the target nodes, and the second step is to sample the neighbors, and the third step is to call toBlock to construct a more memory efficient data structure. So the neighbor sampler actually performed the second step and the third step, but I haven't shown you how to do the first step. Here, I will just use the PyTorch data loader as an example to show you how we can construct to sample the target nodes. I mean, I'm pretty sure most of you have used the PyTorch, so you should be quite familiar with this data load object. The data load object. So basically, what we need to do is we need to provide all the node IDs in the training set as a data set for the PyTorch data loader, and then we need to specify the batch size. Another thing I think it's kind of unique here is we need to define the correlate function, and we use we take advantage of this correlate function and provide this neighbor sampler's sample method. And in this way, after the data loader is generate the samples, the target nodes, if for this mini batch, it will call this sample function to generate to sample the neighbors and construct the block data structure. And then we also need to shuffle the data for each epoch, because this is stochastic gradient descent. So I haven't really talked about the model definition, so I'm not going to implement run this block first. But we use Adam as an optimizer, and then we. Oh, by the way, so I forget so when I talk about the data set, I forget to mention what is the task. Basically, we are going to use PubMed to do a node classification task. So when we evaluate the accuracy, we will just to check how many predicted labels are the true labels. And now we get to the training loop. So the training loop for graph neural network, it actually is very, very similar to most of the other deep learning models. It proceeds with epochs, and then for inside each epoch, we will just we will get a mini batch from the data loader, and every time a data loader returns, it returns multiple blocks, depend on the number of layers we want to run. So if we want to run 2-layer graph sage, then each time it should return 2 blocks. The first block, the source node of the first block actually contains the input features of this graph sage model. And then the output node of the destination node of the second block contains the labels of the target nodes. So in this way, so we get those input nodes and output nodes, and then we get the features and also the labels. And then we run, we pass the features, the blocks, data structure, and the input features to our graph neural network model, which generate the predictions. And then we do use a cross entropy to compute the loss for the training for this node classification task. And then we perform the forward computation and then perform step to update model parameters. Then after, one thing is the inference usually is quite expensive. So we decide to perform the inference for every 5 epochs. And for to perform the inference, we use we call this inference with the SageNet function that performs a mini batch inference on the multi-layer graph sage model. And it will generate some predictions, and then we evaluate the prediction result on the training set, on the validation set and the test set. Okay, now let's go back to the model that the last 2 code block in this notebook. Then after that, we will be able to run the entire mini batch training. So for graph sage, we to define this graph sage multi-layer graph sage model, we define this class called SageNet. And here we want to use DGL's built-in class called SageConv to construct a graph sage. So in the morning session, we already see that we can use the SageConv to construct a multi-layer graph sage for full graph training. And actually, we can use the same the SageConv class to construct a model for mini batch training as well. Because this all our built-in modules supports both the homogeneous graph as well as the bipartite graph. And remember, block is a bipartite graph, so we can so that's why we can easily to perform computation on a block, perform computation of those built-in modules on a mini batch. So so this SageNet actually is actually more general. So we actually allow user to specify the number of layers, and the user needs to define the number of input features, output features, as well as the hidden dimension size. And then we need to define a separate individual SageConv layers for each layer. Sorry, and we need to define create a SageConv object for each layer. And so for the input layer, we need to specify the input features will be the same as the input feature of the model, and the output feature will be the hidden dimension size of the. And then we use mean as the aggregation and ReLU as the activation. So we define the other layers similarly. And then, so for the forward computation, this SageNet will accept accepts a list of block as input, as well as the input features for the first block. So then we iterate over all the blocks in the mini batch, and then propagate the information from the input feature, the first layer towards the last layer, and then which outputs embedding for the target nodes. Now let's take a look at what we do, what we did for this propagation function. There is a little bit of trick I have to mention in when I explain this propagation function. So again, this layer is this SageConv object, and the SageConv accepts. So when we call this layer, we need to pass the graph structure to SageConv, and because this block is a bipartite graph, so we need to provide a tuple of input features. Two elements for the input features. So the first element of the tuple is actually the features for the source nodes. And then the second element is the features of the destination nodes. This layer, this SageConv will perform the message passing in this bipartite graph and generate the embedding. So another thing I have to mention is, so one question is, how do we get the features of the destination node? So if you remember what I mentioned, there is a trick we actually used when we call toBlock. Basically, when we call toBlock to construct a block structure, we put the destination node as in the source node list. So and the destination node, when we place the destination node on the source node list, they are always labeled starting from 0 to the number of destination nodes. So that means when we get this the node features, so the features of the source nodes, we already get the features of the destination nodes. So that's why when we want to get access to it, we can simply slice them from the source node. Sorry, from the source features. Okay, so let's take a look at let's look at the last part, basically how we are going to perform mini batch inference. So we have seen what so in the previous code block, we see how we perform mini batch computation for training. Now, if we want to perform mini batch computation for inference, we have to do it a little bit differently. And instead of we perform the computation of multiple blocks for each mini batch, we actually instead of perform block computation on multiple layers for each mini batch, we actually want to perform the mini batch computation on we want to perform the mini batch computation on all the nodes for one layer first, and then we move on move to the next layer. So then so here we reuse this neighbor sampler, and then we provide this the entire graph, and then we provide we ask the neighbor sampler to sample one block each time. And then we do not want to sample any neighbors. So we just specify the number of the fan out to be the number of nodes in the graph. So the reason the reason is when we actually realized when we if we sample neighbors for inference, we see we found that the performance actually drops. So the better we can estimate the neighbor aggregation result, the more accurate the model will become, and the prediction will become. So that's why we do not want to sample any neighbors for when we perform inference. So then we iterate over the layers first, the SageConv layers first, and then for each inside each layer, we construct mini batches. And in this way, so each time we call this block sampler, which basically is the neighbor sampler, and then we sample for a set of target node, and then this block sampler should only return one block. So we will get one block, and then we perform the propagation computation in this one block, when we pass the input features and also the SageConv model for this layer, which will return the embeddings of the target node, and then we collect all the embeddings for all the nodes in the graph, and then we construct the embeddings of all nodes in the graph afterwards, after we get out of this for loop, which will become the input feature for the next layer. And then we do it, we iterate over all the layers, which will allow us to generate the embeddings of all the nodes in the graph for multi-layer convolution, multi-layer graph stage. And then we return the final result. Okay, so let's execute them. These two blocks, now we can perform now we can really see we can perform the mini batch training. So as we see, and this is actually a CPU instance. So the instance that you get is also a CPU instance. And of course, I mean, this is a really small graph, so it's pretty fast. And after we already performed the 200 iterations. So we get some pretty good accuracy for this data set. Now, maybe I think we have, actually we still have plenty of time. So let's try this. So we now, this time now we are going to use a much larger data set. So this data set will have about 2.4 million nodes and 123 million edges. And when they, this data set is actually Amazon product co-purchasing network, is actually from Open Graph Benchmark. So they already provide a DGL data loader, so we will just import DGL, the OGB, and then get its data loader, which returns this Amazon product co-purchasing network in a format that can be consumed by DGL. And we can see that, okay, so when this data set also has their own predefined data split. So the most of the nodes actually, so they don't have many, they don't have many, the training set is actually is still pretty small. I guess it's the reason is they want to show how, show the benefit of semi-supervised learning. Then most of the data set and data points are actually in the test set. So it has like 2.2 million nodes in the test set. So that's why the inference is much slower. Usually, I was usually this kind of data set should be trained on a GPU instance. But we at this point we don't have a GPU instance, so let's see what we can get. Let's run through all the blocks. I think it will take a while. So maybe I can take questions. By the way, so if you want to try it yourself, I noticed that it's pretty slow to download this data set. The entire data set is about like a 2 or 3 gigabytes, and then it do a lot of pre-processing and to load the data set. So it may take a while if you want to run on this data set yourself. Okay, so yeah, so do you guys have any questions? Otherwise, we will just wait until they print out some accuracy. But I remember it is pretty slow. Or if there's no questions, I mean, you can guys, if you have questions, I mean, if you have any question afterwards, we can just send us emails and we will try to answer all the questions. Otherwise, maybe we can end this session. And thank you everyone for coming to this session come to this session.
Yeah, thanks everyone, and thanks Da. It's pretty late actually in Bay Area, so thanks for the effort. Let's take 30 minutes break, and we will have our last session. That is about applying GNNs to real world applications. So we'll probably start at around 3:40. Yeah.
Hey guys, should we start? It's 4 o'clock. Okay, so let me get out the chat window. Okay, so this is the last session for the tutorial today. Can you hear me speaking? Cool. So this is the last session for the tutorial today, and the content is about DGL on real-world applications. So in the morning, George, Mingjie, Da, and Zizi all talked about lots of use cases for various GNN applications. And here's a brief overview of the non-exhaustive list of what are the possible use cases. So that includes recommender systems, product search, and fraud detection, community detection, et cetera, et cetera. And our current, so this session would focus on one particular scenario, that is recommender systems. And for product search, fraud detection, community detection, we're not going to go through the details. So let's have a brief overview on what is the problem statement for a recommender system first. So for a recommender system, we usually start with a set of users and a set of items, and also a set of interactions between the users and the items, such as whether the user clicked an item, whether the user likes an item, and so on. And so given the interaction history for all the users and all the items, we wish to find that for a given user, what are the most likely items that will be interacted by the user. So now, like the contemporary approach for solving recommender system is called collaborative filtering, and the rationale for collaborative filtering is essentially given a user and an item, and we wish to predict whether the user likes the item or not. We do that by finding these similar users to that particular user and similar items to that particular item, and we look at those similar items and users, and then try to make predictions based on that. And now, like a lot of people are doing collaborative filtering with machine learning instead. So the idea of doing this with machine learning is to represent the users and items with a bunch of latent features, often represented as a high low dimensional vector, or maybe like high dimensional vector. They're latent vectors. So here's an example of how this latent factor model works. So essentially, an item can be described with a set of features such as like how sweet some food is, or like how much calorie does the food have, and so on. And likewise, a user can be described with preferences of the same set of features. So such as like to correspond with the sweetness of a food, the corresponding feature would be essentially how much a user likes the sweet food. And the interaction, so actually the interaction would be like something like how much the user prefers the item. So such preference would be defined by how well the item features match the user preferences. So to express it mathematically, we can represent the item feature as a vector called Vj, and each dimension would represent different latent factor. And similarly, a user can be described with another vector with the same dimensionality as Vj. And the rating on item j by user I that measures the how much the user would prefer this item is defined by the dot product between the user vector and the item vector. So like the dot product would be measuring like how much the user's preference over one latent feature matches the items feature. And to train this whole model to learn meaningful stuff, we would try to minimize the difference between the predicted rating and the ground truth rating. So the ground truth rating is written as Rij, and the UIT-Vj would be the dot product between the user and item vectors. And of course, we can make the model more complicated by adding user-specific and item-specific biases, and maybe like regularization terms on the user embeddings and item embeddings, item vectors. And also we can train this thing stochastically by sampling a mini batch of user item pairs and compute the loss and compute the gradients based on the mini batch loss. So another scenario for recommender system is that previously we talked about how to predict the rating of a user to an item, but sometimes we more often we don't have the the concrete rating of the user to the item. Oftentimes we often only have what are the previous interactions of the user to some of the items. That means we don't have an explicit feedback score of an user item pair. But we can still learn meaningful stuff on this kind of data. So we have this assumption that for a given user I, an item being interacted should have a higher score than another item that was never being interacted. And based on this assumption, we can develop a loss function that compares the score of the user to the interacted item versus the user and the item that was never being interacted. And we try to maximize the difference between the former and the latter. And usually when we compare the interacted item versus the not interacted item, we often since the set of items that was never being interacted is often quite large, during training we often just sample a bunch of items, and we compare the item that was interacted. Let's call it positive items versus those part of items that was never being interacted. Let's call it negative items. And such kind of training strategy is called negative sampling. So essentially, we talked about representing the user and item as vectors. So those vectors can be either themselves learnable parameters or some function over some learnable function over user and item features. It can also be a function over the sequence of interacted items based on, let's say, a recurrent neural network. And of course, we can represent UI and VJ by the output of a graph neural network. So how do we formulate this problem as something related to a graph neural network? So we can observe that the history is often expressed as a user item matrix. And we also know that graphs can also be represented as matrices. So essentially, we can convert this user item matrix into a bipartite graph where users stay on one side as kind of like user nodes, and items stay on another side called as a set of item nodes. And the interactions are represented as edges connecting the users and the items. So we can get a bipartite graph from the interaction history. So explicit feedbacks or like rating predicting the rating of a user to an item then essentially reduces to an edge classification or edge regression problem. That means we predict the property of an edge connecting between the two nodes based on the features on both endpoints as well as the features on the edge itself. And that is called edge classification or edge regression. And for implicit feedback, it is reduced to what we call link prediction. That means to predict whether an edge exists between two nodes. And link prediction is what that was introduced in MeJS tutorial previously. And we will see how we can implement the edge classification and regression in DGL in Notebook later. So here's an example, like I would call it a very classical example of how to do the rating prediction task with a graph neural network. So probably you have already seen this graph in ZZ's tutorial, and I will dive into a little bit more details. So essentially we're representing users and items as an output of a graph neural network. And we all know that graph neural network, the core of the graph neural network is essentially message passing. So here, the user nodes would receive messages from all the item nodes that the user has been previously interacted. And likewise, the items would receive messages from all the users that interacted with it. And how do we compute the message sent from a user to an item? So this equation describes the message sent from item J to user I with a rating R. R means the rating between the rating given by UI to the item VJ. So mu VJ to UI comma R is described as a linear projection of the item features, the feature of the J's item itself, followed by a normalizer. The normalizer can be either like an average or like whatever constant. It's a preset constant. And after we compute the messages, we would try to aggregate all the rating specific messages, and then we perform another aggregation across the different ratings, and then we pass it through a nonlinearity to get the user representation. Yeah, there it is. So, and similarly, we compute the item representation in the same way. The users will send messages to the items, and items will aggregate the messages sent from its neighboring users. And finally, GCMC computes the probability of the user I rating item J with the rating score R by passing through a softmax. So sometimes the users and items may have no features, and in that case, we would make XVJ and XUI themselves learnable parameters. So if you have any questions, please feel free to interrupt me. So although it's expressed as a classification problem, in the notebook we will instead solve it as a regression problem. That is, we are gonna compute the loss by measuring the square difference between the predicted rating, which is UIT, QRVJ, against the ground truth rating. So here's a couple other meaningful aspects to consider in a typical recommender system setting, which includes cold start, meaning, here's a question. If they have no features, can we use identity matrix instead? The answer is yes. So, So the answer is yes, but we usually we usually do not do that. Do that in the exact same way, like representing the item with a one-hot vector. I assume that's I assume that's what you have in mind, like representing the item feature as a one-hot vector. Okay. So essentially yes, but if we have a lot of users and a lot of items, such as maybe we sometimes have billions of users and billions of items, identity matrix doesn't work because it takes too much space. But if we make these XVJ and XUI themselves learnable parameters, then it's essentially equivalent to projecting the one-hot vector to a lower dimensional space by an embedding lookup. I hope that answers your question. Okay, cool. All right, so cold start essentially means that once we train a model, and we deploy it. And sometimes we will observe that new users come in and new items are brought up to the stock. And they sometimes do not have features, or like do not have interactions, or have a few interactions. So in that case, how would the model work? How can the model generalize to new users and items? That remains an open question. And also bias correction, meaning that like in real world cases, the training data set that collects the previous user and item interactions usually comes from the result of a previous recommender system. So essentially, you deploy. So essentially, you have a historical recommender system working that recommends products to the users, and that will introduce some kind of selection bias to the data set. And if you train, so when you train a new model, like how much should you care about this selection bias? And if you care about the selection bias, how do you mitigate that bias? That's also an open problem. And also sometimes you would care about diversity of recommendation to a user, because by always recommending the same product to the user, maybe the user gets bored and not interested in your platform anymore, which is not good. But this is also an open question. And also, like another thing we need to combat with is to like detect and deal with fabricated explicit feedbacks. Like sometimes, like a competitor would dump a bunch of like fake ratings or fake reviews, and we need to combat those. Okay, and here's a non-exhaustive list of recommender system models that showed success that succeeded in either industry or academic data sets. So PinSage is a pretty well-known model that's already deployed in Pinterest platform, and that's doing similar item recommendations, saw successes. And Star GCN is a model that tries to deal with the cold start problem. And here are another models called, for instance, knowledge graph attention networks, knowledge graph convolutional networks. They are all using the knowledge base as an auxiliary graph that connects. So previously we have a user item bipartite graph, but so in these two models, we not only have this user item bipartite graph, we also have a knowledge graph that represents the relation between the user, the relations between the items and another item. And likewise, we can also include social network information between users and users. And the same thing can also be solved with graph neural networks. So in my opinion, the graph neural network, the biggest advantage of graph neural network is that you can combine multiple information together and train it in a unified framework. So you can essentially combine the knowledge graph, the interaction bipartite graph, and the social network graph together. And this year we also have seen another graph neural network called inductive matrix completion, and there's a lot of other papers. Okay, so far, do we have any questions? Otherwise, we'll go to the hands-on session. Okay, so I guess I'll go ahead. So before actually looking into the notebook, let me quickly introduce how to do mini batch training on rating prediction with a graph neural network. So oftentimes the interaction history would be pretty large. So essentially we'll have, like in real world cases, we have millions or billions of users and millions of items, and also like billions or trillions of interactions. So it doesn't make sense if we train a graph neural network on the entire graph. So in the previous tutorial, Da has shared how to train a graph neural network on a node classification task stochastically by sampling mini batches. And we are going to do the same thing, except that we are going to do rating prediction. So let's look at this small problem. So given the graph in the figure, so we wish to predict the rating of selected edge mini batch with a one layer graph neural network. So the selected edge are bolded, meaning that we are going to predict the rating between the U3 and I5 as well as U4 and I5. So in DGL, we typically do things like the following. So we first construct a miniature graph that only consists of the edges in the mini batch and also the nodes that were being used in the mini batch. So in this case, only U3, U4, and I5 are included in this miniature graph. So I'm dubbing it as a pair graph. So the point of constructing this pair graph is that once we get the rating of U3, U4, and I5, DGL provides a nice function called apply edges that takes in the graph and also the source features, also the features at both endpoints, and it will compute the edge features based on the endpoint features in parallel. So essentially, once we compute the user and item features, we can use apply edges to compute the score of the corresponding interactions. So once we have the pair graph, the next thing we need to do is to figure out what are the necessary nodes, what are the nodes that are needed to compute U3, U4, and I5. And that was done by finding the neighbors of U3, U4, and I5, which makes the graph look like this. So this dependency graph is similar to what Da has mentioned previously in the node classification task, except that it's now a bipartite graph instead of a homogeneous graph. And once we find the neighbors, of the necessary node, once we find the neighbors of the needed nodes, we can convert it with a, once we have the necessary nodes, we can convert this computation dependency with DGL.2 block, which was also introduced in the previous tutorial. And after using that, we can just do a normal net message passing on the block instead to do like more efficient message passing. So one trick that we also observed useful is that when we are training our model to predict the rating of, let's say, U3 and I5 and also U4 and I5, we don't want to tell the model that these edges exist because during testing, the interactions in the test set doesn't exist in the training set. And if we still include, so essentially, like if we are training to predict U3 and I5 and U4 and I5, including both edges in this computation dependency would somehow tell the model that there is an edge existing between the U3 and I5 as well as U4 and I5, and such an information leakage would cause a bit of overfitting. So if we remove these edges, it can somehow reduce overfitting, as observed in our experiments. And here's a complete computation procedure, which contains a lot of items, but we will go through the items one by one in the Jupyter notebook. So let's open the applications directory and find the rexis.ipynb Jupyter notebook. and you will see a notebook talking about recommender system with GNNs. So can you see the notebook? Okay, cool. Cool. So in our hands-on, we will use movie lens 100K dataset. It is tiny, but it suffices for the demonstration purpose. And also to further simplify stuff in our tutorial, we will not be considering new users and items. So the first thing we need to do is to loading the tables describing the user features, item features, as well as the user item interactions in both training and testing sets. They reside in 4 tables respectively, and we load them using pandas. Maybe I should restart this whole thing. So we load them using pandas. And here is a preview of the tables. So you can see that training data consists of 4 columns: user ID, item ID, rating, and timestamp, which we're not going to use for now. And user data would contain, so the columns are not named, but not titled, but that doesn't matter. So the first column is the user ID, followed by age, gender, occupation, as well as zip code. So for our tutorial, we're not going to use zip code. We're only going to use we're only going to use age, gender, and occupation. And for item data, we have title, we have item ID, title, which we're not going to use, and also the I assume this is the date of date. I assume this is the date, but we're not going to use that. This is also like an empty column. The URL to the IMDb, we're also not going to use it. And the last 19 columns are binary masks representing the 19 genres listed, 19 movie genres listed in the movie lens document. So I can't remember which is which, but like each 0-1 row represents a binary mask. And we're gonna represent the item features with we're gonna use the binary genre mask as the item feature. So to construct a user item bipartite graph, we need this thing called a heterogeneous graph in DGL. So previously, in previous tutorials, we all, like the graph we have seen are they only have one node type and one edge type. And for heterogeneous graph, we have multiple node types and multiple edge types. So with movie lens 100K loaded, we'll see how to build a heterogeneous graph from it. So first, we try to because the user ID and item ID are not starting from 0 and they are not consecutive, we need to relabel it first by using pandas code, by converting the user IDs into categories and extracting the category codes as a relabeled user ID. And after that, we construct a DGL.header graph by specifying a dictionary of relations and the actual connections between the source nodes and destination nodes. So here, we can see that we specify a relation called user watched item, meaning that there will be a set of user nodes and there will be a set of item nodes, and the connection is specified by train user IDs and corresponding train item IDs. And because the DGL graphs are directional, so we need to manually insert an inverse relation from items to users as well. So we're specifying. So we're specifying item watched by user relation that starts from train item IDs to train user IDs. So yeah, so here is how we create a heterogeneous graph. And by specifying heterogeneous graph in this way, we know that there are two node types called users and items. And also there are two edge types called watched and watched by. So so in DGL, a heterogeneous graph is often associated with what we call a meta graph. And the meta graph describes how edge types connect with different node types. And it is fully specified in this keys of the dictionary. If you guys are familiar with the literature of heterogeneous information network, then you should then meta graphs in DGL is equivalent to the schema of the HIN. And here is a visualization of the meta graph. So you can see that there's a user node, there are user nodes, there are item nodes, there is an edge connecting from user to item, and there's another edge type connecting from item to user. It's a bidirectional, but Network X rendered the bidirectional edges in this way. And also by printing the graph, we can see that the graph has 1,680 items and 943 users. And it has more than 90,000 interactions representing users, watched, and item. So after we construct the heterogeneous graph by specifying the topology, we now need to assign the corresponding node features to users and item nodes. And here lists the all the features we are going to use. So we are pre-processing the user and item features, and meanwhile we are finding what are the possible what are the number of categories for each categorical variable, and how many genres are there in each item. And after that, we set the node features and edge features with this kind of syntax. So previously we have seen the syntax called graph.nData and graph.eData. So in heterogeneous graph, the setting is quite similar, except that now we have this graph.nodes followed by a specification of node type dot data h, and we specified by this statement we specify that the age feature of all the user nodes should be like this, and the gender feature of all the users would be like this, and likewise the genre feature of item nodes would look like this, and also to set the edge features of the graph, we have this kind of syntax as well. So we can actually print out what is the oops, sorry, didn't run it. Sorry, never mind. Okay. So So here's how we specify the user features, item features. So after we construct the heterogeneous graph, we now need to consider how we are gonna sample mini batches and how we are gonna define our model. So as we explained, as Da explained previously, the actual mini batch sampling of the seed nodes are not done in DGL itself. It is done by PyTorch data loader. And similarly, we're also gonna give the job of sampling ratings between users and items to the data loader as well. So here we are constructing a training data set which consists of a triplet of users, items, and ratings, as well as the test data set containing the test user IDs, item IDs, and ratings. And after that, we are gonna go for the mini batch sampler for GCMC. So let's go back to the slides for a while. So the first thing we're gonna do is to sample a mini batch of edges, which is done by the PyTorch data loader. And the mini batch of edges would be represented as the batch argument. And we are gonna get the user vector, item vector, and rating vector from the mini batch. And after that, we're gonna construct a paragraph, which looks like this. And this code creates a paragraph we have seen. And after we create this kind of paragraph, we need to also further compact the graph so that only the necessary users and IDs that are users and items that appear in the mini batch is included. So essentially, these two statements accomplish this construct a paragraph from those edges step. And after that, we are going to construct the computation dependency graph and transform the dependency graph this DGL.2 block. And that is done with the self.construct blocks function. And the implementation is here. So first, we take all the neighbors of the seeds of the seed nodes. The seed nodes are the nodes that appeared in the paragraph specified here. And once we have the seed nodes, we find the in subgraph, which means the like all the neighbors that are predecessors of the seed nodes, meaning that all the like we are going to find all the edges that has an that connect to the seed nodes. And we are also going to find the edge IDs in the original graph. We're also going to remove the edges connecting in the mini batch from this neighboring graph. So this whole chunk of code is doing what we are seeing here. It removes the edges in the mini batch that is usually in I5, U4, and I5 to this. And after this, we are creating a block for future message passing. We're also going to copy the ratings from the original graph to this block. And after this, we are also going to copy node features from original graph to the sampled block. So any questions? Okay, so now let's look at how we're going to define our graph convolutional matrix completion model. So recall that the So recall that the formulation of graph convolutional matrix completion is here. Okay, so the first thing we're going to do is to implement the message passing module in essentially essentially equation 1, 2, 3. And the message passing module is implemented here in GCMC conv. We can see that we have for a direction connecting, let's say for the user watched item relation, we are going to have the users on the source and items on the destination, and we're going to assign user features and item features and compute the messages by multiplying the source feature with a rating specific matrix, which is done here in this compute message function. And after we compute the messages, we are going to aggregate the messages. We are going to aggregate the messages on the edges by an average into this edge nav feature. And after the aggregation, we are going to update the representations of the output items or users by concatenating the item features themselves as well as the aggregation, followed by a nonlinear projection. So this completes the 1, 2, 3 step for GCMC. And once we specify how we are going to do graph convolutional matrix completion for a single relation, or for a single direction, we are going to apply this same module to both directions. So remember that we have a user watched item relation as well as an inverse relation called item watched by user, and that could be accomplished with what we call heterograph conv. So in heterogeneous graph convolution, you specify a convolution module for each edge type. So here we are using this GCMC conv, and of course, if you want to use a normal graph convolution, if you want to use graph sage convolution, you can also replace them with DGL.n and .sage conv or similar stuff. And another thing you need to specify is the aggregation strategy on each node type along incoming edge types. But in our case, since users only receive messages from items and items only receive messages from users, this option doesn't matter here in our case. And the forward function operates on a block, which represents the computation dependency of a single GCMC layer. So we have a block, we have input user features, and we have input item features. And we just specify what are the source features, what are the destination features, and we specify the result by passing this source destination feature pairs into heterogeneous graph convolution with the block, and that's it. So if you guys still remember how we did for large graph node classification, you might notice that the structure is very similar. You have the source feature, you have this destination features, you have this convolution, you pass in the pair of source destination features, except that the block here is from a heterogeneous graph, and also source features and destination features are dictionaries. A dictionary of a dictionary of node types and node features. So after we define the GCMC layer, we finally go to this the entire model that does the input feature transformation, the message passing, and also the actual rating prediction step. So here, we're starting from a learnable user embedding and item embedding for each of the user nodes and item nodes. And we start from the learnable embeddings, and we add the transform embed. We add the transform features from, let's say, user age, user gender, user occupation, and item genres. And we add all the transform features up as the input to the graph convolutional, actual graph convolutional network. And here we are performing a actual heterogeneous GCMC convolution by iterating over the blocks and GCMC layers. And we are doing message passing here in this loop. So after this loop, we will get the output of user embeddings and item embeddings after the graph neural network, and we are doing a final linear projection to get the latent representation of each user and each item in the mini batch. And once we have this, we are going to copy these user embeddings and item output embeddings into the paragraph here, and we are going to compute the dot product between the user embeddings and item embeddings with this function, with this apply edges function. And finally, we're going to return the feature R residing on the edges of the paragraph. And that's how we're going to do the forward propagation of the GCMC model. Oops, I didn't run this. So after we define the graph convolutional network itself, we're defining evaluation metric for measuring how well our model performs. And here is a training loop. So essentially, we're defining a sampler. We're defining a mini batch sampler for rating prediction. And we are specifying a data loader that combines the user item rating triplets into a list of blocks as well as a paragraph. We have seen here. So essentially, like for the computation procedure, we need a paragraph and a list of blocks, and that will be returned by the data loader by the sampler.sample function. So we're also defining a model that specifies the number of users, number of items, the hidden dimensionality, the number of ratings, and also the number of layers. And we specify the optimizer. The training procedure is quite straightforward then. So essentially, we start from the blocks, we compute the output user embedding and item embedding, and we compute the predicted rating by this compute score method. And we measure the mean squared error, and we compute the gradient to the mean squared error. For evaluation, it's pretty similar as well. So instead of iterating over this train data loader, we iterate over the test data loader. And we essentially do the same thing. Oops, mini batch sample is not defined. Assume I didn't do this. Okay, so so we can see this rating prediction script running. Okay, so although I will not go through the details of how to do implicit feedbacks, I will briefly mention how to do mini batch sampling on implicit feedback dataset. Although I'm not gonna provide an end-to-end code for implicit feedback recommendation. So DGL now provides a lot of models, including GCMC and also relational graph convolutional networks for link prediction and also PinSage. They're all available in our repository. So if you're interested in how to actually do implicit feedbacks or like link predictions on a real world data, you can. So feel free to check it out. So here, like we are mentioning this idea of negative sampling. Stop this first. So we have this idea of negative sampling that compares the users and item and an interacted item versus the user and the item that was never being interacted. And here's the loss. Here's essentially the hinge loss that encourages the score of the positive item to be always higher than the negative items by at least one. So in graph learning, the computation steps is very similar to edge classification, except that instead of creating one paragraph for rating prediction, you are going to create two paragraphs, one that contains all the positive interactions and another paragraph that contains all the negative interactions. And of course, you're going to compact both graphs, and constructing blocks is the same as the rating prediction, and message propagation is also the same. And after message propagation, you are going to copy output to both paragraphs, both the positive and negative paragraph, and compute the preference with apply edges on positive paragraph and negative paragraph separately. And after that, you can compare the scores between the positive and negative paragraphs. And here is an example implementation of link prediction mini batch sampler. And you will notice that we are returning a positive paragraph, a negative paragraph, and a list of blocks. So much for the notebook. So do you have any questions? So if you guys don't have the do not have any questions for now, you're always free to visit our GitHub repository. Oh, someone raised hand. Okay.
Yeah. So hello, I had a question regarding like how like am I audible?
Yes. Hello? Yes, I hear you.
Yeah. Yeah. So I had a question regarding like you told that you are using negative sampling over here. So how do you determine the hyperparameter or like the number of negative samples which you are choosing? I mean, just a small doubt.
So yeah, so good question. So the negative items are sampled here. So here we are only sampling one negative item for each positive example. But of course, you can like specify the number of negative items by specifying the number of negative examples per positive example in this way.
Okay, so is it that taking like empirically, is it that taking same as the number of positive, same number of samples as negative samples as the positive ones, does it perform better? Just asking. I mean. in case of.
Oh, so you're asking like how do we decide the number of negative examples per positive example?
Yeah, exactly.
Oh, okay. So it's we usually tune it as a hyperparameter.
Okay, so okay, sure. Okay, right. Thank you.
Any more questions? Actually, how do I see if someone raised a hand or not? So okay, so I guess you can always ask questions in the either the GitHub issue, or either the GitHub issues if you find any like feature requests or bugs, or you can always visit the discuss forum in discuss.dgl.ai. And also, oh, okay.
Yeah, Chen, go ahead.
Oh, okay. And also, like we also recently established a Slack channel. So yeah.
Yeah, and all the materials are available online in the GitHub. So you guys can always review the materials and go through all the notebook locally. And yeah, I think that completes today's tutorial.
Yeah. Thanks
Cool.
for watching.
Yeah, thanks everyone for attending. Yeah, see you. Bye-bye.